risk category influence each other. Next. So we can now we should see about the science and technology. Of course, the science and technology bring many benefit and many advantages. But if we don't do the prudent governance on that, can create, like many disadvantages. So what's the science and technology according to what's a World Economic Forum? It's like sustainable computing, wearable plant sensor, 3D printing, yeah, one of the additive manufacturing, advanced material, agri-technology, biotechnology, batteries, blockchain, etc. Next. So we can see the future of the technology, such as data policy, digital identity, yeah, superconductivity, and metaverse, digital transformation of business, precision medicine, and many more. Next. So we would like to see about the 3D printing according to the World Economic Forum. 3D printing and what its connection to broader social and environmental concern. So I just give the example, the connection from 3D printing and bioprinting, such as Prof. Andi said before about the biomedical engineering. Yeah, so 3D printing and bioprinting, yeah, the connection and the environmental concerns, there, according to the World Economic Forum, there are 6 factors: Fourth Industrial Revolution, advanced manufacturing, advanced material, of course, justice and law. Yeah, justice and law, and healthcare and biotechnology. But overall, when we see the 3D printing, we can see the connection with the space, travel and tourism, yeah, supply chains, advanced manufacturing, future of the environment, future of consumption, and etc. That this all factor can create possibility to do more research for the good of human being. Next. And what about the education itself? So when we see the education, because of the global issue, because of the rapid development of the technology, so we can see that education also has a link to broader social technology and environmental concern, and of course influenced by the industry. So when I just give example education and its connection to digital fluency, not again digital literacy, but we need digital fluency and STEM skill. So the factor that can impact to the education is the digital economy, values, data science, artificial intelligence, future of work, science, the fourth industrial revolution, innovation, future of computing. But when we see the whole, according to the World Economic Forum, that we have to concern about like economic progress, such as agile governance, and all, of course, like youth of perspective, systemic racism, yeah, and what against arts and culture, virtual and augmented reality, pandemic, preparedness and response, ergonomic progress, digital communication, social protection, human rights and taxes. So this also gives us, possibility, opportunity to do more research on that. Next. So what's about ERP? Why I would like to share ERP? Because ERP is part of the additive manufacturing, if I'm not wrong. So ERP, enterprise resource planning, can help how to manage the institution. So when I do the literature review, So I can see that ERP benefit for higher education institution is a lot and already implemented in many education institutions. Next. So this is the ERP system in higher education institution. So I just, refer to the work of Blerta Abasi Chausi et al. 2018. So ERP system in higher education institution, we need like learning management system, library management system, facility management system, customer relationship management system, and grant management system. So when we see this kind of the research to how the ERP can help or to manage education institution, we can, refer to this research. Next. So this is, they define the functional requirement of ERP, yeah, become 30 functional. So the functional requirement describing the behavior of the system of ERP as it relates to the system functionality. So the first one, institution profile, second one, staff profile, until the number 30, education and labor market observatory. Next. This is the non-functional requirement of ERP system. So the non-functional requirement of ERP system can elaborate a performance characteristic of the system. So there are 24 according to them. So what's the first one? Accessibility. Yes, we know, all of us, we know that. And the second one, capacity, current, and forecast. And the third one, compliance, until the last one is SLA, service level agreement. So what's the service level agreement between the institution with their stakeholder? Next. Because of the, the rapid development of the technology, so we need to provide our students the soft skills such as computational thinking. When we see the interconnection between the science and technology with the, the connection with the environmental, social, and many more, they said that we need future computation. So to prepare our students to face the near future, we need to provide them computational thinking. What's the computational thinking? Computational thinking is the flexibility and understanding of the natural world as sum of logical operation that can be recorded using software. How to we embed in our education system this kind of skill, yeah, and also the computational thinking comprises of 4 pillars. The first one, decomposition, pattern matching, that's really relevant with the additive manufacturing, and also abstraction and algorithm or automation. So computational thinking is about the mental skill and how to practice more in our education. Next. And I would like to share about the 4th Industry 4.0 paradigm, yeah, because it's related also to the education, digital era, and again with additive manufacturing. So this is from the research I take from the IEEE Access 2021, it's the new one paper. The characteristic and sub-feature of Industrial 4.1. It's the feature, there are 6 features. It's flexibility, adaptability, and fault tolerance, against, yeah, and self-adaptability, learning characteristic, and reconfigurability. And such as for adaptability adaptability is really important because we have, have this skill. The world changing rapidly, so we have to more adapt to the change. So adaptability, the sub-feature is agile, agility, technology, change ability, interoperability, responsiveness, and digitize ability. So this is, can also open the door to do more research in education. Next. The example of the education and the training course already done in Europe for the, like the for the woodworking sector and the furniture, they found that they have to provide not only the young person, but also the adult with this kind of knowledge and skill and also the competency. So they develop wood training course. Next. So this the module, yeah. This the module. There are 5 modules, yeah. And what they share to the worker, it's about the 3D printing, yeah, and also augmented reality, sensor and wearable sensor, and robotic, yeah, Internet of Things, big data and analytic, etc. How to they distributed the cost and how the process in the class, they choose on the right hand side, yeah. On the left hand side, it's the traditional one, yeah. The traditional one, they process transfer, the knowledge transfer between the lecturer or the instructor to the student, but it's the traditional one, but they did on the right hand side. So that's the training path network implemented in the InfoWood platform. Next. So I would like to share about the technological spotlight of digital transformation in tertiary education. So the current technology trends concerned and deployed in the educational environments are, of course, the emerging technologies such as artificial, Internet of Things, blockchains, and etc. So what's the research direction and what's the benefit? One example is behavioral analytics using an artificial intelligence model. And what's the benefit? Identify high-risk students for dropout in first year. So we can predict from the first year using artificial intelligence that's which the student have high risk to more dropout in the first year or low risk. That's also the example, the technology implementation in tertiary education. Next. This overview implementation of SMAC, social, mobile, analytic, and cloud to the education, such as social platform. Focus on use of platform for student engagement. What's the benefit? To enhance student academic performance, learning anytime and anywhere. Okay, so what's the benefit using blockchain in education? So we have like the smart contract, certification, copyright management, and also when we see like trusted educational framework. Yeah, this blockchain is already implemented in Europe for the credit transfer. For credit transfer, for the knowledge certificate, and for the smart contract. Okay, next. What for useful of the IoT in education? So the benefit is energy saving and environmental sustainability, automatically detecting the stress level in student, enhance student motivation, attention and engagement, help design an adaptive curriculum and personalized learning, and many more. Next. So now I would like to share about what I found from the journal about the additive manufacturing social impact. So the area of social impact for additive manufacturing is, of course, the intellectual property right, because we can print everything, anything, yeah, anywhere. And impact to the health, quality of life and safety, business model and market, work, education and skill. Next. So many slides to share.
Yeah, you can we
jump to,
right.
okay.
Thank you.
Next. Yeah, okay, this topic and activity in additive manufacturing education and training program. Next. And this is what's the augmented reality cyber physical system and feedback control to improve additive manufacturing. Next. Blockchains to improve additive manufacturing. Next. Next. Benefit of blockchains for AM supply chains. Of course, there are 6 they got from their research. Next. This is, how to improve search engine in additive manufacturing. Yeah, because, it's really make it easier to do the manufacture when we can create a smart search engine. Next. Okay, next. This is IoT, yeah, to predictive maintenance of 3D printing. Next. Okay, next. Next again. I would like to jump to the Udayana University. Okay, next. Okay, this is what we already done in Udayana University. ERP. ERP we already implemented, but we try to do more to make our what's managing the institution more efficiently. So we already developed one system, integrated system. We call it AMISU. AMISU, it's really, comprised of academic, planning, financial system, human resources. There are totally 58 information systems and more than 100 websites of Udayana domain. Next. This is the example for the research, research information system, and also for the, administrative information system. Next. This is the example for, academic bureau. Yeah, we have like registration, payment, and etc. Next. Then, for our, learning management system, we already developed. We call it OASE. Next. This is an example of we already implemented ERP in Udayana University. Next. This is how we, not adopt, but similar with InfoWood, already training system for the wood industry. So we also develop in Udayana University. We call it Digital Society. What the module? The module we provide the first year student about blockchain, digital communication. We provide them about the what's cloud computing, digital leadership, and again digital ethic and big data and etc. Okay, next. So this is our my last slide. I would like to share from all the literature review and what already done in Udayana University, the recommendation, the interconnection between the education and how to face the rapid development of technology. Our recommendation is in education, we always keep the collaboration with the industry and because now the gap is wide between education in Indonesia and the industry, and of course we need put an embed in our education about the future global issue, local wisdom, good and bad perspective. Because now when we ask the student do the research for their final year, we always ask what's the benefit, but we never ask what the disadvantage of your idea. When the idea used by the bad people. That's really because, you know, we face our world today because the research and the industry, the previous one, it's not thinking about what's the damage occur to the environment. So we need to provide good and bad perspective. Yeah, I adopt with the IEEE education because they afraid of the development of artificial intelligence. Yeah, the artificial intelligence, if the bad people use it, it can be damaged. Yeah, and we also put moral, ethic, attitude, and behavior on our education. We put how to provide the skill, adaptability, and future skill to our student. And of course the STEAM. And for the environmental, we put green technology and emerging technology, environment, sustainable development, and intelligence. It's really relevant with Trihita Karana. When you see on the, the banner, yeah, we see Trihita Karana. Trihita Karana, we always, balance our relationship from human to human, human to environment, and human to the Almighty, to the God. Okay, that's all from my sharing, and I hope that you can learn from that also. Thank you very much.
Thank you, Belina. Any question? I think it's very important for us scientists in which that the morality and the intention to use our technology, our research for something not good for the humanity. I think that's the lesson we learned from the speak. Any question from the floor? Yes, Ibu?
Hello. First of all, I would like to say that I really like your presentation. I think it's inspiring that how can you integrate artificial intelligence, Internet of Things into education. And as a student myself, I was wondering if there's any possibility that you include students in the developing of those integration, because I know that in developing artificial intelligence, blockchain, and the Internet of Things, it would take quite some time, and I'm curious, how long does it take for Udayana University to develop the database, and can students also collaborate in developing those systems? Thank you.
Thank you. Go ahead, Ibu.
Okay, thank you. Yes, until now, not all the students what's learned about the artificial intelligence, because in Udayana University we have 13 faculties from humaniora, humanity until the engineering faculty. So in engineering faculty, not all also the study program put artificial intelligence itself in their curriculum. So we need to to change the curriculum, more adapt for the rapid change of the technology. But we already implement one course that we call it digital society. So in digital society, we provide one topic, artificial intelligence, to the student. And all the students of Udayana University can take this. So when they do their task, the assignment, they can collaborate in one team with a different discipline of area. So they can learn from each other. But the implementation is not so massive. So I would like, if the colleagues agree in Faculty of Engineering, we would like to have a course that all the first year students can do together the project, such as in Japan, when I went to Japan 2019, they already have in Faculty of Engineering, all first year student went to the lab to develop robotic. Yeah, all the engineering students from the mechanical, electrical, industrial, they work together, develop a robotic for the humanity. That's all. Thank you.
Okay, that's really great. I'm glad to hear that. Well, thank you for the answer.
Okay, thank you.
Thank you. I think one question only. I understand somebody else also asked, but I think we go to the next program. Right? Thank you, Ibu Lina.
Thank you.
Very good presentation. Next, we would like to Professor Rianti Dewi Slamet Ariobimo, Dean of Faculty of Industrial Technology, Trisakti University, will present recent advances in iron casting, case study of thin wall ductile iron. Ibu, go ahead. Want to use mic, Ibu?
Yes. Wait, I just open this first. Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. Warm welcome and greetings, Shalom, Om Swastiastu, Namo Buddhaya, Rahayu. Good morning, everyone. I hope all of you have enjoyed visiting Bali. And as I was asked here by Professor Arif, thank you very much for this opportunity. And first of all, we would like to convey our congratulations for this event. And before I started our research, please allow me to first of all give a little bit profile about Universitas Trisakti. As you know, Universitas Trisakti is a private university, but owned by the government. It was established in 29th of November 1965, and then due to the raid in 1998, Universitas Trisakti is known as the Campus Pahlawan Reformasi or Reformation Campus. Now we got 9 faculty. There is law, economics and business, medical, dentistry, and we got 4 engineering faculties. Yeah, the same like ITB, Pak. We have a lot of engineering deans, and one of it is my faculty. Our faculty is, we know it as a Faculty of Industrial Technology, or we call it as FTI. In FTI is established in 1980, but 2 of the departments were there together with the university. That is the mechanical engineering and the electrical engineering.
Both are together with the Universitas Trisakti in 1965. And then now we still have 4 departments, that is mechanical, electrical, industrial, and also informatics. That's why we always call Trisakti, the FTE of Trisakti is one package. Because we have the old generations, like the mechanical, electricals, but we also have the modern science that is in informatics. So join together there. And now we have, now we have 10 study program. We have another one, it's 9. The newest one is the PSPPI, the Profession for Engineers, and the PhD for Industrial Technology, TI. We invite all of you who need to have the profession title. Please join us in Trisakti because we have the PSPPI, and also if you want to get our doctorate for industrial technology. Okay, now I'm entering to our research. Thank you for the committee for letting us share our research. But before I started, I think I have to tell of you that this one is not as heavy as the previous speakers, because this is a very, very light informations, and I do hope that all of you can understand and enjoy, and maybe can also give us some more opinion or some more parameters and everything. The title is The Recent Advance in Iron Casting, Case Study of Thin Wall Ductile Iron. This research was moderated by the Physical Metallurgy Laboratory, which inside there's a ductile iron research group. And the question will be, why everyone have shifting to aluminum, composite, other modern materials, and also to shifting manufacturing to the AM, why we are still thinking about ductile iron? As all of you know, that since 1948, industrial has used ductile iron, and it has been used until now. And because of the uniqueness, specialties, ductile iron has been used for so many years, still 1950s, in the form of austemper ductile iron in many forms of sectors, especially the automotive sectors. Now, what is austemper ductile iron? Austemper ductile iron is ductile iron plus austempering process. So when we are talking about austemper ductile iron, we should talk about ductile iron. It's one package. Okay. Now, as you all know, you can search in internet when you want to find out about austemper ductile iron or ductile iron. You can see so many specialties, so many advantages you will get when you use these materials. But this material got one very bad weakness. That is, oops, what happened? Oh. Oops. Huh? Sorry. What weakness is weight. Why? Because first of all, ductile iron is not classified as light materials. Secondly, because they are designed with a very heavy, bulky design. So, if we want ductile iron to keep on being used in industry, we should try to think how we can lighter this. Because why? Because the research from SCARM has found out that if you can reduce around 100 kilos of weight, then the consumption of energy will at 0.425 kilometers for 1 liters. So in here we see that how weight will connection with the energy consumption. In here, a fuel. And Hornung in Boku has found out that 100 kilograms of decreasing will increase 0.5 liter for 100 kilometers. This is why, this is what makes everyone turn out their face from ductile iron. Only because of weight. And now what we are going to do is we are trying to lighter the design of ductile iron. Now this is what the advantage you can get if you use ductile iron. And this is one of the research that has shown that we could reduce 200 grams of the weight of connecting rod. This is connecting rod for combustion engine with 2 cylinder. And this is our roadmaps. So the research group have begun the research of austemper ductile iron since 1993. And now is still working out. And this roadmaps goes to 2025. I think we will be prolong this again. And this is the research project, the recent research project we make. First of all, we are trying to apply the lighter design, which is known as thin wall ductile iron. Thin wall casting design. Thin wall casting design is a design that part of or whole component you produce have the thickness of maximum 5 millimeters according to Caldera and 3 millimeters according to Stefanescu. Now we are using the Stefanescu, that is 3 millimeters, and here in our research group, we have managed to make it until 1 millimeters. 1 millimeters, Pak. We started by making a plate, and after we make a plate, we have the casting design. Now we have applied the design to this, to this. And now we are still doing these two, the motor frames and the connecting rod. And we all do it industrial base. So all the casting process and all the austempering process is done not in the laboratory, but we done it in the factory, in the foundry. What is the research aim? Our research aim is, first of all, we want ductile iron to come back. Yeah. This is what I thought. Ductile iron is like a beautiful, smart, healthy, rich girls. He's abandoned because she is getting fatter. Yeah, that's why we have to put her on diet. So everyone will come and adore her again.
Very up as analogy, Bu.
And also this is the second one. Now we are talking about advanced materials, modern materials. So yeah, this is like old marble need polishing. Ductile iron need another design, need another polishing, so he can compete with another new modern materials. Why? Yeah, because ductile iron has a lot of advantage that everybody forgot. And this is technology development. Yeah, you were smiling because like cooking pasta Indonesian style. What I mean is that technology is everywhere, developing everywhere. Every country has developed technology, but is it suited for us? Is this really for us? So what we are trying to do, we are trying to apply a technology, worldwide technology, but based on what needed in Indonesia. And in fact, our tempered ductile iron we do develop in here is in fact prepared for the small scale foundry. That's why later you will see why everything is done very, very simple. Only use the sand casting, graffiti casting, only that. We don't want to talk about high tech. Why? Because we want to give this to the small foundry, casting foundry. And this one, we want this to take care of the sustainability of ductile iron foundry, especially the small-scale industry. According to the data we received from HAPLI, Himpunan Ahli Pengecoran Indonesia, we have 200 foundry, 157 is the cast iron foundry, and 22% of it is a small and home industry. So this is what we want to save. Sorry. And the last one, I think it's a little bit, to euphoria, the implementation of SDGs number 12. Why? Because ductile iron is energy saving in the process, and also when you use it. So both during the production and during the application. That is why we are still not turn off our face from ductile iron. This is the first research project, the connecting rod. We started from plate. We make the casting design, we establish the casting design, and we have patented for this. And then we apply this to make the connecting rod. And this is the design. The first one is 4 millimeters. The thickness of the I-beam is 4 millimeters. The first step, we go to 3 millimeters. And with this reduction, according to the simulation, we reduce about 18 grams. But in experiment, we found out it's to be 36. After that, we try to make it to 2 millimeters, and then 1 millimeter, sorry. Oops. And then 1 millimeters. Why have to be step by step? Because we have to ensure that what we do in here will not disturb the properties. Still fulfilling the requirement of the design. That is why during the research, we also do the analysis both of the for the damping properties, all the stress, strain, everything. And then we also use simulation, casting simulation first before we do the real experiment. After that, this is the result, as you see. Yeah, we have succeeded in 3 millimeters and 2 millimeters, and we still have to do some more repairment in 1 millimeters. But what happening in 1 millimeters is not because of the design. It's more to the foundry's problems. Yeah. This is our first casting. So when we have established the design, we go to a very small scale foundry. We ask them to make this. Why we go to small scale? Because we want to ensure that our design can be made by small scale industry. And if small scale industry can make it, big industry, medium industry, it's a very little things. It's very easy for them. because they get equipment and everything. But small industry, no. This is the the factor, the foundry. You can see it's very, see the furnace is also very small. And when compared to the design, we match between the simulation with the result. And as I mentioned, we mentioned before that all the problems happen, all the defects is not because of the design. It's more to the process. And this is the microstructures we have. Also the compression test. Why compression? Because we do it for connecting rod, and we have analyzed that the most important things is compression. And then this is the compression strength. Yeah, and this is both, sorry, I forgot to say this. This is both for ductile iron and ADI, both. Because we use a ductile iron, then we call it as thin wall ductile iron and thin wall austemper ductile iron. This is the compression strength. And this is a special holder that we should make. Why? Because during the compression test, we really put the connecting rod in there. We are not taking the sample. And we use the tension by using the tensile machine, but give contradicts, yeah. And this is also the fatigue machine testing we have to build, because we really want to do we want to check, yeah, to really check.
The life.
Yeah, the lifetime and everything. Okay. Now, our second project now is making the frame for the electric motors.
Oh,
yeah, but because this is started on 2001, yeah, then COVID happened. So until now, we are not able to do the experiment yet. But now it's ongoing in GTK Funindo. Now this is the design, the porosity and everything, and finally we have chosen the latest improvement. And I think in February we will see how the experiment will result. In here, what we do is we reduce the thickness of the housing, of the frame, from 4 millimeters to 2 millimeters. And this is the summary of the result. And the next research we have to still to do is, first of all, we have to repair this. But thanks to God, this already. But I haven't put it here.
Checked,
yeah,
you haven't checked the compressive strength, right?
Yeah, and this is the next model. We are going to eliminate all the body of the I-beam.
Wow.
So it will be lighter and lighter again. And then for the housing, we will do the experimental. And as for the 3D printing, we also need this. What we need is, because we need to make the pattern. The pattern to make the mold. Yeah, we will ask the help for the 3D printing, and we are planning to join with the one other labs in our mechanical engineering departments. And that is all. Thank you very much. I hope I didn't make you more sleepy or
Not
stressed.
at all, Ibu. Ibu, you are champion of the small enterprises. Any question from the floor? Just only one. Go ahead.
Thank you so much, Prof. Rianti, for your presentation. I am Basuki, I am from industry. Actually, I am from Toyota Indonesia. I think your presentation very interesting, that related with casting. for your information that Toyota Indonesia also have two kind of casting processes. That we have iron casting, actually in Sunter plant, and also aluminum. The interesting thing that you presented today related with you made reducing for materials, yeah. That as Toyota Indonesia, and also hopefully it will be very beneficial to our supplier for maybe first tier or second tier, which is some of our supplier also small scale industry. I think that's will be very beneficial, yeah. But sometimes we have the struggle while we are find out the idea to reduce our material costs or another ideas to reduce costs. But frankly, I think we feel that our linkage between industry and academic,
right?
yeah, that's very frankly, we feel very not so good. So maybe in the next we can make some communication with academic, and we can get some solution or any ideas to improve our processes. Thank you.
Okay.
Thank you very much. Of course, we are welcoming you, Bapak. If you want to come and discuss, please do. And we also, our lab also have, every year we got a special, we call it PKM, Pak. It's CSR, but it's not right CSR for the company. We give some
incentive type of thing.
Some insight to the industry and sharing like that. If you want to join, we will send you the invitation because it's free, and it's done by Zoom, so you can do it everywhere. And one thing we would like to remind all of you here, everyone now is changing their face to aluminium. But please do remember, yesterday Prof. Satrio has shown us how aluminium productions. Yeah, not many people understand that aluminium production need a very high energy. From bauxite to become the primary, secondary, and everything, the process is very complicated. And if you, there is several journals that discuss of it, because I was challenged by the aluminium side regarding my statement, and we have found several journals that support the energy used in aluminium is really very high, and even the comparison between the TCO2, the CO,
Carbon dioxide,
carbon active is very high. So please don't see aluminium as one of a way. Yeah, you have to find another way if you really want to reduce the energy use. That's why we are working very hard to improve
ductile
iron.
casting.
Yeah,
Right. Yeah, you were right.
Yeah. Maybe that's all, Pak. Thank you.
Thank you, Bu Yuryanti. Big applause. Champion of small enterprises. Next, we would like to invite Professor Takayuki Shiraiwa from University of Tokyo in Japan, presenting acoustic emission method for materials reliability application in additive manufacturing. The floor is yours.
Thank you very much for kind introduction. And first of all, thank you very much for inviting me. So, it's my pleasure to have this opportunity. So, yes, I'm from the University of Tokyo. I'm here instead of Professor Enoki, and we are working in the E-Asia project with Professor Aliyev. And the research topic of this project is nanolayer materials. But today I will talk about a different topic, acoustic emission method for materials reliability and its application to additive manufacturing. At first, I'd like to introduce our department. Our department is materials engineering. And in our department, there are 3 courses: a biomaterial course, eco-material course, and nanomaterial course. And we have about 40 faculty members. And I'm here, eco-material course. Eco-material means almost a structural material. But I have many collaboration work with biomaterial and nanomaterial, so the boundary is not clear, but there are 3 courses. And in our department, we have some scholarship program for international students. So if any student interested in studying our university, you can check the website of this program. Program name is IME program. Maybe you can find this website by searching IME program in Google or something. And this is the website of our laboratory. Our laboratory is Enoki Shiraiwa Lab. Official name is Reliable Materials Engineering Lab. In our laboratory, we are doing experiment and development for materials reliability. So here is additive manufacturing, and this is friction stir welding of metallic material. And also we are doing the mechanical testing of bio devices. This is a simulation, but we are doing experiment of biomaterial. And so here we are doing a tension test, compression test, fatigue test of metallic material, and we are analyzing the deformation and fracture of these materials. And also we are developing the wireless sensor network. This is my PhD thesis. So we developed a wireless sensor network for monitoring the fatigue and corrosion condition of infrastructure. Okay, so I'd like to start the research topic. So today, I'd like to talk about acoustic emission and its application to additive manufacturing. And if time permits, so I will talk the other application of AE. Okay, so acoustic emission AE method is a kind of a non-destructive evaluation method. AE is elastic wave emission. It is generated by dislocation, twinning, phase transformation, and microcracking of materials. And in some situation, you can hear the AE directly. So if you bend a tin, you can hear the tin cry. You know? So this is a kind of AE due to the twin deformation. And if you do a compression test of concrete or something, you can hear some sound. It is also AE. It is generated by crack initiation and propagation. But the sound we can hear is roughly from 20 to 20 kilohertz. But in AE method, we focus on from 100 kilohertz to 1 megahertz. Because this frequency matches well to the time scale of dislocation and microcracking of materials. And this is easy to separate from low frequency noise. So in AE method, we attach the AE sensor to the material, and the material itself emits the ultrasonic sound, and the sensor converts the elastic wave to electrical signal. And we amplify and filter and record the signal. So this is a passive and dynamic method. And similar non-destructive evaluation method is UT, ultrasonic testing. Both methods use ultrasonic sound, but the principle is very different. So in this method, we emit the ultrasonic sound from this one. So we can find a pre-existing defect. But in A method, we cannot find pre-existing defect. We can find the defect generation in real time in A method, and it's opposite in the UT. So UT is an active and static method. So this is complementary. And A method is widely used in various fields. For example, the non-destructive testing of material, structure health monitoring, detection of gas leaks, abnormal electrical discharge, and health monitoring of plants like a tomato. Because in tomatoes, so some cavitation occurs when the tomato is not healthy, so we can find the elastic wave. So we can monitor the health condition of the plant. Also, the gas leak and the electrical discharge generates the elastic wave, and we can monitoring the condition by AE. So AE method has a lot of advantages. The time resolution is sub-micron or sub-microsecond, and it's very sensitive to surface displacement, and it can evaluate the inside of material, and this is non-destructive method. And if we prepare multiple sensors, we can find the location, time and location of the AE source. This is similar to earthquake analysis. In earthquake analysis, we find the time, location, and the magnitude of epicenter. So ISAM. So if we put several A sensors, we can find the time, location, and the magnitude of micro cracking or something. And it can be used simultaneously with other observation methods, like digital image correlation, X-ray, and neutron diffraction. But there is a strong disadvantage. So A method requires analysis to correlate with the physical phenomena, because A method is not a direct method. This is an indirect method, so we have to correlate with the physical phenomena. So this is the theory of A method. A signal we measure is V, and this is a convolutional integral of SGD, and D is A source. So we have to deconvolute this signal with a sensor response and the green function of specimen. So this is a little bit complicated process. Okay, so I will talk about the application about additive manufacturing. So in our research, we are focusing on the metallic material, laser powder bed fusion process. The micro defect in the laser powder bed fusion process include the cracks, porosities, borings, melted particles, and delamination. Cracks and porosities are caused by excessive heat input, and the boring and the unmelted particle are caused by insufficient heat input, and the delamination is caused by residual stress. It is depends on the specimen shape. And the purpose of our research is to detect the defect generation by repeated melting and solidification by A monitoring during the manufacturing process. So, as I explained, AE is a physical phenomenon which release elastic energy when micro defect occurs in a solid material. The A method is a non-destructive evaluation method using a wave, and it is very similar to the analysis of earthquake. In earthquake, we can find the location of the hypocenter and the magnitude of earthquake. Also in A method, we can find the location, time, and magnitude of a micro defect. So we say A is an earthquake in the material. So we have developed the A measurement system by ourselves. So in a conventional system, the target was structural health monitoring, and recording was conducted by event discretely. But in our system, the target is materials processing monitoring. So in this process, the environment is very noisy. Maybe you can imagine. So in a material processing, the environment is very noisy. So we record the all A waveform continuously and apply the frequency filter. So we improved hardware and software, and so this is an example of a waveform. Maybe you cannot find the A signal here, but if we apply the frequency filter, we can find this small A signal. So here is a low frequency noise, and here is a high frequency noise. But after applying the filter, we can find this small A signal. And also, we developed a wireless A measurement system to realize the A monitoring in the chamber of a additive manufacturing machine. In this system, the continuous sampling and the waveform transmission was conducted in a sensor node, and the data is transmitted by Wi-Fi, and a waveform analysis is conducted in a high-speed PC outside the chamber. Using this system, it is easy to try a monitoring without changing the LPBF machine. So first, I tried the 1D and 2D LPBF. This is a single layer test. So this is substrate, and we tried a single track test and a multi-track test here. And here is a acoustic emission sensor. We used heat-resistant type sensor. The material is asteroid X. This is a kind of a nickel superalloy. And we changed the laser conditions. And this is a result of a comparison between X-ray CT image and A events. This is single track test. And here is a starting point of a laser, and the laser scanned like this. And here is a 2.5 millimeter. This corresponding to the 10 millisecond of a laser scan. And this is corresponding A waveform. So if you compare the two images, so you can see the several A events here. And the A event occurred about 0.5 millisecond after the pore generation. So this is due to the cracking from the pore. So all A events occurred around the laser spot. And after that, we did A source location. We can find the location of A source by using the differences in wave arrival times, because we put the two A sensors, so we can find the location of AE. So this is laser position history. So laser started here to laser scanned here to here, and each bubble represents the A events. The color is A amplitude, and position is position of A, location of A event, and the time of A events. So all A events were located at the position of the laser spot. And this is the result of the A source location in a 2D. So this is the result of a multi-track test. So this is a mild laser condition. This is intermediate condition. This is a strong laser conditions. So you can find the many A events around here and here. So many A events occurred at the edge of the object. This is because the laser turned back here, like this. So turn back here. So this position is subjected to two times heat input. So there are many pores, so many A events occurred here. This is a result of X-ray CT image. So you can, so here is object. So here is edge. So laser scan like this, and the pore is here, and we can find the corresponding A event. And these A events corresponding to the cracks in the object. So it was shown that A event corresponding to the pore and cracks in the object. And finally, we conducted the 3D additive manufacturing. This is a multi-layer test. We fabricated the 8 blocks, and we attached the 4 A sensors, and we did a location using these 4 A sensors. And we changed the laser condition for each block. This is a movie of our experiment. This is our A measurement system, and this is additive manufacturing machine. So the machine is coating the powder, and so here is laser. So and the A sensor is behind this substrate. So during the process, we can find the A event in real time. Actually, it is very noisy, but after applying some filter, we can find the A event very clearly. And this is the result of a 3D additive manufacturing. This plot represents the A energy in each object. X-axis is time, and the y-axis is A energy. And the number 4, 7, 6 is excessive heat condition. So this is a bad condition, and this is good condition. So we can distinguish the poor and the bad condition by comparing the A energy in real time. And this is a typical laser condition map. So this is the scan speed and the laser power. So basically, we try to go in the upper right direction to improve the speed of manufacturing. But there is a limitation by the defect generation. So it is important to find this boundary. So in this study, we showed that using A method, we can find this boundary. And this is A source location results. So now we are comparing this A result and the X-ray CT image. And also we are now developing the more easier A monitoring system. So in this system, A sensor node and A sensor are implemented in this box. So A monitoring can be enabled by simply placing a box between the substrate and the stage. So now we don't need to prepare a special substrate, and no need to attach and detach the sensors for each fabrication, and no contamination of the powder due to the sensor or cable attached to the substrate with instant adhesive. And this is very recent results. So now we tried the same technique to additive manufacturing of a titanium alloy. So we fabricated 4 cube with a lattice pattern, tunnel pattern, and support, and inverted pyramid. And this is a result. So we found that the many A events occurred around the tunnel like this. So this is summary on additive manufacturing. So practical A monitoring method for the LPBF process was developed. And most of the A events during the LPBF process were located at the laser spot. And the A events were detected under excessive heat input condition and correlated with crack and porosities by X-ray CT observation. And multiple objects with different fabrication conditions could be evaluated by A method simultaneously. This method can be used regardless of the material, size, or shape of object. Okay, and if I have time, I continue my presentation.
It just Is that another quite a lot?
Yeah, maybe I have 20 page.
Okay, I think if you can shorten, that would be great.
Okay, so I will briefly explain the second topic. So second topic is a application in other materials research. That is a plastic deformation of magnesium alloy. Because I'm working on materials engineering, so I'm interested in plastic deformation of metallic material. And magnesium alloy is very important to reduce the weight of structure. So a source in the magnesium alloy is a slip deformation, twin deformation, cracking, and friction. And in our study, we found that the formation and annihilation of twinning is the main source of AE in magnesium alloy. And we can evaluate the fracture toughness by the AE signal. And now we are interested in a magnesium alloy with long period stacking ordered phase, LPSO phase. This is magnesium zinc yttrium alloy. So it has very high strength. So this is elongation and strength. The conventional magnesium alloy is here, but this alloy is here. So strength is about 600 megapascal. This is stronger than conventional magnesium alloy. And this strength, this high strength is due to the kink deformation. This is like a microscale backlink deformation. So we tried to evaluate the kink deformation behavior by AE. So we prepared alpha magnesium single phase and LPSO single phase material and two-phase alloys. And we measure the acoustic emission signal in this single phase alloy. And we used the A signal as a training data and applied the machine learning technique. And we evaluate the kink and twin deformation in the two-phase alloys. And this is material. This is single-phase material, and this is a two-phase material. This is very strong material. And we did a compression test and put the A sensor here. And we did a deconvolution analysis. And this is surface observation. We observed a lot of twinning in the magnesium alloy. This is single alpha magnesium phase material. And this is single LPSO phase material. In the LPSO phase material, we observed many kink band deformation, kink band generation. And we count this number of twin and the number of kink bands in each material. And this is a high-speed observation. We directly observed the twin generation with very high-speed observation. Frame rate is very high, so 5 million frames per second. And we observed the velocity of the twin generation. It is 2,900 meters per second. And this is the result of kink deformation. It is about 300 meters per second. And this is the statistical data of velocity of twin and kink bands. And this is A result. We recorded a lot of AE. So this is the result of our LPSO phase. And the frequency characteristics of AE is different between alpha magnesium phase and LPSO phase. So we used this data as a training data of our machine learning method. This is the convolution analysis result. I skipped here. So finally, we applied the machine learning technique to evaluate the kink and twin deformation in two-phase material. So this is two-phase material. Here is alpha phase, and here is the LPSO phase. And we observed the kink band deformation in the LPSO phase. and count its twin and kink band, and measure the aquatic emission, and apply the machine learning technique to separate the AE due to twin and kink by machine learning technique. This is the result of the machine learning. So we successfully separated the A signal to twin and kink. So we clearly find that the twin occurred around here, yield point. This is summary on the magnesium alloy, and this is last slide of my presentation. So at first I talked about a method, and in additive manufacturing, the high temperature gradient associated with laser can lead to the formation of defect and unique microstructure, and it can be evaluated by AE. And AE is also effective to analyzing the microscopic deformation and microscopic fracture in material. That's all. Thank you very much.
Thank you, Professor Takayuki. It seems that your AE has been successfully in many alloy. Right, any question from the floor? All right, from Bapak dari Toyota.
Thank you, Prof. Sirayuwasang, for your presentation. I am Basuki from Toyota Indonesia. I'm very interested with your presentation related with acoustic emission method. Actually, we have a problem in our process. The first is in the machining process, crankshaft, for crankshaft. That in the crankshaft, we have the hardening or induction hardening, yakireki. Hardening process, yes, that we use induction hardening. So we should check at least three items. The first is related with hardness, then crack. The third one is depth of hardness, fukasa. But the problem is related with the fukasa check or depth of hardness check. That we should cut the product, and it takes maybe 1 or 2 days.
It's become a destructive test.
Yeah,
basically.
and
right,
of course the product will not be used anymore. So my question is it possible to do to use acoustic emission method to solve this kind of problem? Or do you have any solution? This is also related with the casting process also, that in the casting process we have the problem that actually we should detect by cut the product. For the example, related with the some blowhole defect. Sometimes blowhole defect we can detect only when the process already in the stage of machining process. So already run
almost
through.
finishing.
Yeah, already many processes that we pass through already, and also the product cannot use anymore. So that is the question.
It's become rejected product basically.
Thank you.
Thank you very much for the question. Actually, A method is effective for detect the defect generation. So after the process, we cannot find the defect. So maybe it is important to use a multiple method to check the defect and like hardness or something. And, actually, we maybe not I put here, but we have applied the acoustic method to machining process. So and the machining process of composite material, and in such a application we can find the clock generation during the machining process. So
I think that's very useful then. We are looking forward to your collaboration.
maybe we can talk later.
Any more questions? Please remain on the stage. We would like to invite another speaker from the plenary, Ibu Lina, Pak Andi, to the stage. Okay. Well, Ibu Lina, and Pak Arif to present a token of appreciation as well as the certificate. Well, just right in time, Pak Andi. Please come to the stage. Yes, Ibu Lina? Okay. Yeah. Pak Andi? Applause. And next, Ibu Lina. Please join me for the applause. Actually, the third one, Ibu Rianti, but you have yours yesterday, so we go directly to Professor Takayuki Shiraiwa. Professor Takayuki Shiraiwa. Join me for the applause for Professor Takayuki Shiraiwa. Thank you for the distinguished guest, please.
All right.
We will take the pictures of all of you.
Oh, yeah.
Okay, one for the speakers only, and the second one is for the audience as well. For group pictures, we will just be seated in our place, and maybe they have to come back to. Bapak diambilnya dari situ aja, jadi kita di sini.
Let's give applause again to our distinguished speaker. I do have one announcement. It's really important for the banquet later tonight. So I think as I've already announced, for those of you whose name tag has stamp on the back, so you guys are invited to for the banquet tonight at, well, we will leave from here, but if you want
Yes.
you are coming,
Right.
RSVP. If you could confirm that you are coming to the banquet to Dr. Endang Juwana, maybe Pak Udif could stand up. Please help and let Dr. Juwana know that you'll be coming, or maybe you'll not be coming, so that we can arrange the exact transportation and everything we need, like the exact amount. So yeah, so I think that's. Is there maybe not something that is not clear about the arrangement for tonight's banquet? Especially if they are not coming. If you are coming, that's okay. You don't need to inform.
What time we will meet here for those that coming to the dinner?
Yeah, so we will end the last session this afternoon. We'll end probably about 5, maybe 5:10. So yeah, so I think we'll be around here 5:10, and then we'll make our own way with the transportation. And if the cloud is already clear up, we hope to see the sunset.
Yes.
In Jimbaran, because they say it's really beautiful. I haven't been there.
Yeah, sunset is great. Hopefully no cloudy.
We try. So
Yeah.
So by the end of the last session, please just hang around here. We will arrange transportation for all of us to go to the
Jimbaran.
banquet place. The banquet, well, probably we will start at 7. But yeah, we'll have to go from here to there, and it takes
About 45 minutes without traffic jam.
So, so if you want to go there by yourself, please feel free to contact Dr. Juwana, and he can give you the address. All right, so I think that's all the announcement for today. Take some photo.
Yeah, group pictures. Please come back to.
All right. Oh. Oh, yeah. Question? Oh no. Oh. So we'll have a break, and I think we should be back here because we are already way behind schedule. So now it's 10:55. So maybe we'll try to come back here by 11:15. We kind of have like a short break because we are already 45 minutes behind schedule. So 11:15, please come back for the next session. Thank you. nanti yang oh iya 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 oke lah kayaknya tapi bingung orang ini sekolah sampai minggu lalu ngomong nanti ini kasih email ke saya oh ini namanya tapi terus saya follow up tapi karena namanya nggak saya angkat saya nggak ngerti apa-apa All right. Welcome back. I think we'll start our session soon. So this session is about additive manufacturing, enabling novel engineering and emerging design. So this is what I said earlier about like one of the theme of this conference is about additive manufacturing that can enable design of mechanical system, for example, that is so far impossible, but yet it will actually enhance the performance. I mean, heat exchange is probably the most obvious example. So we'll hear from a couple of examples where with additive manufacturing, what is before impossible to make, now it's being possible, and it's actually enhancing the performance of the material. With that, let's start with keynote seminar by Dr. Mark John from IHPC, that's Institute of High Performance Computing, that is part of ISTA in Singapore. Is Mark ready? Oh, okay. There you go. Hey, Mark, how are you?
Hi, I'm well. Thank you very much for the introduction, Arif. And sorry I can't be there in person, but thanks so much for giving me the opportunity to talk a little bit to get to you guys today. So I'm going to be talking about sort of material science.
Mark, not yet.
Sorry.
Sorry, I was just about to introduce you. I haven't introduced you. I haven't introduced.
Okay, thank you.
Yeah, it's okay. Just a brief introduction. Dr. Mark John and I have been friends for a long time. I used to be in Singapore. We collaborate a lot. Dr. Mark John graduated from UC Berkeley for his PhD, and then he's also a material scientist. And today his talk, the title is Role of Mesostructural Defects in the Mechanical Properties of Coupons Printed with Laser Powder Bed Fusion. Okay, Mark, sorry, Dr. John, without further ado, the floor is yours.
Okay, sorry about that, Arif. Thanks again for the introduction and for the invitation. So I'm going to be talking about some of the material science aspects of failure in powder bed AM materials. So let me see. So first, let me just tell you about some of the collaborators that I've been working with over the past few years on this work. So most of what's I'll be showing has been the work of my colleagues from IHPC, Dr. Karthikeya Joshi and Dr. Mustafa Jamshidian. But we've worked with other institutes in ISTA, including the Advanced Manufacturing and Technology Center, as well as the Nanyang Technological University in Singapore. I also have some collaborators that have moved on to France, to the University of Technology of Belfort, Montbéliard, and to Thailand, to King Mongkut's University of Technology, Thonburi. So basically, I'll just remind you a little bit of something that you've seen a lot of over the past 2 days, which is that the laser bed powder bed fusion process, right? And so the reason that I'm bringing this up again is to remind you that the process itself actually will make very unique material structures, both at the microscale from the columnar grains and segregation during the solidification process, as well as the fact that you have this layered structure because of the powder, as well as mesoscale features. So you can have the melt pools as well as porosity due to the melting process. And so one of the key aspects of the mechanical properties is that they actually will depend on all of these scales of the material. So one thing that I wanted to point out is that when you're trying to understand which defects are important, it doesn't always mean that if you have a lot of defects, it will be weak. There are circumstances where you have a small number of defects that are very, very dangerous, right? And so this is what I've been calling quality versus quantity. So quality is how influential are these defects, and quantity is how many of them are there. So the point is that these defects can be distributed non-uniformly. So even though we try to describe them statistically by, by variables such as average pore shape, average pore volume, that a particular pore might be the most important. And so this is just a paper from the literature showing how the presence of defects can cause very wide spreads in strains of failure, even though the porosity, the nominal porosity of these parts is quite similar, and that they attribute to the distribution of those pores. So we tried to revisit this problem experimentally as well as computationally. And so the first thing we wanted to try to do is to quantify the porosity in these printed parts. And so I'm showing here a few of the standard methods. One is a micrograph method where you cross-section the piece, and then you use a microscope to basically see where all of the pores are on that cross-section. And then another method here, which is microcomputed X-ray tomography, where you get to see the full three-dimensional structure. So one of the interesting aspects of this is that even though these methods agree pretty well for high density, low porosity materials, they tend to start to diverge once you get to higher and higher porosities. And you can see here, this is the micrograph method, and this is the micro CT method on the same material. And so that you can see that there's like this factor of 2 difference. And what I want to convey here is that these methods, they're not necessarily wrong, because even though that they're disagreeing, but they're measuring different things. And so what I just want to point out is that when you do try to measure defects and quantify them with things like porosity, with measures like porosity, you have to remember what the method that you're using is. So for instance, if you're to try to measure the porosity of this using Archimedes, where you would take this sample and put it into some liquid and see how much volume it displaces. And that way you get the effective density, and you back calculate out what the porosity must be. So the difference is that when you use that method, if you have trapped powder, trapped unmelted powder inside of the material, that'll count as solid material because it is solid. But if you do a micrograph, when you do the polishing, all that powder gets knocked out. And so again, what I wanted to try to convey is that when we're trying to understand what the consequences of these defects are, we have to be able to quantify them appropriately, right? So we then tried to measure the mechanical properties of these materials as well, and we found that by changing the scan strategy, we are able to get pretty wide range of mechanical properties. As we get denser and denser, we tend to get higher and higher strengths. So, but we also observe that there's a fair amount of stochasticity, a fair amount of spread. So we wanted to try to build some kind of computational model that could help us to understand this. To do that, we first needed to understand what the processes were that were going on. So we used microscopy to check the cross-sections to see what did the failure surface look like for these different scan strategies. And so you can, even though you can see there's a lot of residual unmelted powder, you can also see that there are these sorts of evidence of ductile failure as well. And so we was decided to try to use ductile fracture mechanics to try to understand the distribution of strengths of these materials. So looking back, this is a very classical kind of problem that has been studied by many, many people, and you probably learned about it in freshman year as well. But the point is that people like to understand the ductile breakdown of material using this relatively simple picture. And so they basically think that once you start out with the material, it will have some impurities or inclusions. Those will start to, as you pull on the material, those inclusions will start to debond from the matrix, and that will cause voids to start to nucleate. As you pull more, those voids will then start to grow. Then after those voids start to grow, they'll then start to localize. And what I mean by that is that the edges of those voids will then start to stretch more. Then you might have voids starting to interact with each other, causing them to eventually coalesce and cause failure in the material. So people have tried to understand this with continuum plasticity kinds of studies or kinds of models. And one sort of more recent aspect of it that's not as much appreciated is that the spatial distribution of those voids can also affect the properties too. And so if you have like a small cluster of voids, it can also affect the mechanical properties, even if you have the same nominal porosity. So, but with another key to this as well was that when you look at the growth of a particular void, and if you think about the growth and you try to calculate what that growth of a particular void is, and you imagine that the deformation of the matrix can be described with that ductile failure criteria, that this void will also grow according to the same laws as normal. So in other words, that we can have a separation of length scale that lets us treat the growth of large pores and the growth of those kinds of pores that are from ductile failure to using the same tool. So what we've done is to apply this two-scale defect model to try to understand the structure, the experimental structure of the pores. And so what we did was we took micrographs and then took cross sections of those and took those cross sections and digitized them, and then we put a void at each of the pores that we see in the matrix. We then modeled the matrix using a classical ductile failure criteria called the Gerson-Tvergon-Niemann model. And basically, we were able to simulate the deformation of these experimentally derived mesostructures, and were able to predict their strength. So we did this both using micrographs, where we took a single plane. We also did this using micro CT, where the microcomputer tomography, where we took two-dimensional slices of this as well, and we found that we had pretty similar results. So the point that I wanted to show is that the experimental spread in the properties of yield stress and failure strain are shown by these dots that are circled by ellipses. The little X's refer to the horizontally pulled samples, and the little pluses refer to vertically pulled samples through simulation. And what I'd like to show is that, even though we're using a really crude approximation for the materials model, we're looking at 2D, we're looking at very simple plasticity models, where we are able to get the yield stress trends and the trends in failure strain. And interestingly, we're not only getting the trends in the average value of the failure strain, we're also getting the trends in the spreads. And so we're able to see that those values are spread out as we get to closer to perfect, to fully dense materials. So there's a few details that are kind of interesting about it. And so one of the details I want to point out is that when you get to this level, that the details of how you implement the model tend to become more and more important. And that's also part of the reason that we think that there's a spread. So one example is that if we were to model this with periodic boundaries compared to modeling it with fixed boundaries, we actually see that there's a very different response. And part of that is because the distance to the next pore, or the distance to the surface, is actually very different for these two different simulation strategies. So that's sort of the reason that we think that there's a lot of spread in this in the fully dense region, even though things are still governed by by this porosity. That the details of how the distribution is actually are very difficult to incorporate into a model. And so that's why we think the spread is big. So one of the interesting, and so you can see this in a different way. And so what we show here is we show some of the different iterations of this. And so we see that when you have very low porosity compared to very high porosity, the failure for a very high porosity limit, it's actually dominated by the large voids. For the very low porosity, it's still dominated by the voids, but it's more about the linkage of the shear bands rather than just large pores causing cracks. So we then tried to understand a little bit more about how do you describe metrics for how to understand porosity. And so one of the things that we did here is we tried to use like a data science kind of approach, where we used a tool called a Pearson correlation coefficient to try to see how well do some traditional measures of the distribution correlates to properties such as failure strain and the yield stress. And we found that what was interesting is that a lot of the traditional measures, such as the number density of porosity, actually don't really influence the failure strain as much as this value chi, which is basically a distance between pores. And so I just wanted to go through this story to try to, and we also tested to make sure that these measures are consistent between the slices. And so even though we did even though we're taking only a two-dimensional slice of the material, that the way that for our samples, we found that two-dimensional slice was enough. So I just want to show you this story to show you that these kinds of mesostructural defects can be very important, and that you have to be able to understand both the distribution as well as the number of defects in order to understand how they can affect the mechanical properties. So I think the next question would be, can we, if we know that, can we engineer the arrangement of defects to alter the mechanical properties? And to try to answer that question, I think maybe it's easier to try to think about it with a different material system. And so one of the problems about porosity, of course, is that it is a little bit difficult to control the spatial arrangement. But there is other mesostructural features, such as melt pool boundaries, where they are very strongly affected, or where they are very strongly affected by our choice in process parameters. And so in this particular system, aluminum silicon, there's something called cellulose solidification that causes some coarse silicon to form at the melt pool boundaries. And so it turns out that this embrittles this boundary. And so when you print up a material, that those boundaries end up being important. And so because that melt pool structure is governed by the scan strategy, that they can affect the mechanical properties. And specifically here, the fracture toughness or crack propagation resistance, right? And so the point is that those boundaries are chemically distinct, and those silicon precipitates can end up coarsening and basically cause failure to happen preferentially along these boundaries. So the point is that if we know this phenomenon, can we try to understand how to engineer material to increase its fracture toughness, for instance, right? So what we tried to do is we tried to build a simulation or a model to try to understand what the role of these boundaries are in the structure, and try to use that to design a new material. So basically, we tried to go back to the fracture mechanics, and so there's an extension of fracture mechanics called small kink theory, and this basically relates the local fracture toughness to the far-field fracture toughness, and for a crack that is not quite straight, right? That's kinked slightly. And so basically you can use this model to try to understand how much how hard it is for a crack to propagate if it's kinked, right? And so you can also go and eventually figure out that this kink angle can cause that there's a critical kink angle for that crack to stay inside like a soft interface compared to just progressing forward. So basically the idea is that if we follow this condition, then we know that the crack will want to follow the interface. Otherwise, if that boundary is not really very weak, it'll just fracture normally. And so we're able to extend this model to the melt pool geometries. And we also wanted to test it computationally. And so we performed a finite element simulation using something called an embedded cell model, where we took this kind of mesostructure and then we applied a fracture toughness test to this mesostructure to try to make sure that our analysis was sensible. So we found that this computational model was able to replicate the trends in simulation, that if you take a material and you try to crack it, have the crack go perpendicular to the build direction compared to along the build direction, you can get a very, very strong difference in the expected fracture toughness, right? And so this gave us a lot of confidence in our methodology. So we then tried to use this to with different types of melt pool geometries, and we were able to find that for a crack propagating through a material, that we're able to see that there are certain good directions and bad directions, good directions and weak directions in terms of fracture propagation. So by changing the melt pool geometry, we're able to change the shape of these curves as well. So one thing that we also need to remember is we need to be able to bring in the fact that we are using an additive process as well. And that even though that we're trying to modify the melt pools, we might still introduce porosity. So this is just a classic kind of way of looking at the generation of porosity during printing. If you use a laser power that's too low, you'll get incomplete melting, which will lead to something called lack of fusion porosity. If you put in too high of an energy, you'll introduce something called overmelting. So this will give something called keyholing porosity. So we actually, even though we're trying to engineer the melt pool geometry, we only have a certain range of doing it. And so the point is that we wanted to try to understand what are the limits that we can modify the toughness. And so, as I was saying before, if we want to reduce the lack of fusion, lack of fusion defects, we want to make sure that there's no incomplete melting. And so we did some simulations of the melt pool geometries to try to find the regions for which they'll overlap. We also wanted to try to avoid keyholing, and so we took this condition from that's well believed in the literature, and we found that there's, for high energy levels, this area here is actually not is actually forbidden. And so the point is that these kinds of constraints also will affect how much we can increase the properties of material by modifying the melt pool geometries. So I think that's more or less what I want to share from this this work. And I just wanted to quickly summarize that I've been just talking about the mechanical properties and how they relate to some of the internal structure of this material. So in particular, I was focusing on what I call mesostructures, which are larger than microstructures like grain boundaries, but smaller than the scale of the coupon. And I was showing how even very simple 2D models are able to capture and predict some of the properties that you see in experiment. And I was also trying to give some hope that we can use these mesostructures to engineer the properties of materials for the new applications. So thanks a lot for your attention. I hope you found this again, and I'd be happy to take some questions. So thanks again.
All right, thanks, Mark. The paper is open for question. All right, well, I have a question, Mark. So I think earlier you said that having defects is not necessarily making it weak. So can you elaborate a little bit on that? And I think, am I right saying that if we can actually engineer the defect following a certain pattern, it's actually maybe it will deflect the crack, for example, in some crack situation. Yeah, that's yeah. Maybe you can elaborate a little bit more.
Yeah, exactly, Arif. Thanks. Yeah, so I was trying to explain that a little bit with this melt pool problem, right? And so because that you have a laser powder bed fusion built material, you can't really get rid of the melt pools, right? I mean, like, those are really part of the as printed structure, right? So, but I think what I'm saying is that, you know, like, even though you have those melt pools, you still can use them to engineer new properties. And so one of the things that's kind of that you can think about that's kind of a little bit multi-scale is that the things that control strength are not necessarily the things that control toughness and vice versa. And so generally you can make things that are super strong, but they tend to be very brittle. And you can make things that are super ductile, but they tend to be very weak. And I think that this is a situation where it allows you to do engineering of both ends sort of independently. So you can engineer the property of the grains themselves separately, and so you can try to increase strength through the grain scale strength. But then, if the toughness is determined by the melt pool structure, then you can change that sort of independently, and so you may have an opportunity to make materials that are better than what we were able to make previously. Thanks for the question, Arif.
All right. Thanks, Dr. Mark John. Let's give another applause for Mark. Thank you, Mark. We'll have some certificate and a token of appreciation for you. I'll mail it to you. All right. And for the remaining of the session, Dr. Joanna will be the chair because I will be the speaker.
Thanks, Pak Arif. The next speaker is actually our chair. So you already know him very well from yesterday. So I didn't really need to introduce him again. So I just read his title for today. The title of the talk is Impact Resistance and Tough, Novel Helicoidally Fiber-Based Architecture Materials. So the time is yours, Prof. Arif.
Thank you, Pandang. All right. Thanks, Pandang, for the introduction. The title may not be exactly the same, but the content is the same. All right. I'm going to talk about how, with additive manufacturing, we can enable functionality of materials that hasn't been possible before. As I said, this is actually a very core theme of additive manufacturing for material scientists like me. That is basically, with additive manufacturing, we try to create extraordinary or even mechanical properties that see Mark, the earlier speaker, Dr. Mark John, and this, you can see that we are trying to, using additive manufacturing, we are trying to engineer material properties.
Please use the mic for the Zoom people.
All right. Okay. Thanks. All right. So yeah, that's me actually. A few years ago when I was in MIT, you can see that building. I think that's Frank Gehry design. I mean, it looks like you have paper that you just. Yeah. I mean, okay. That's not important. All right. So this material is actually inspired by Mantis ductile club. That's certain kind of sea creature, and then the bio inspiration is actually very common for material scientists, but Mantis shrimp ductile club. The structure is actually very very difficult. I mean, it's not. It's up until 5 years ago, it's just not possible to fabricate. But in this research that I started when I was in MIT, we are able to do that using what we call electrospinning based additive manufacturing. So I'll talk a little bit about the inspiration, but most importantly, I'll talk about the additive manufacturing aspect of it, and then I'll talk about what kind of performance or properties of the material that haven't been possible before, but it is now because of additive manufacturing. All right, so as you can see, this is actually not, this particular structure is actually in Mantis, but actually this kind of 3D architecture is actually not that extraordinary. I mean, well, if you have been to Singapore, you probably like chili crab like me. So, I mean, if you can, I mean, the shell of crab, you can see is actually very hard, even though it's actually just made out of like minerals, nothing much more than chalk, right? But it is very hard. In this case of Mantis shrimp ductile club, is actually this is actually sea creature that can actually hit their other animal, like very high impact strength. And people have been studying this. I think that paper was actually 2015, and they correlate that impact property, very high impact property, is related to the 3D architecture that is shown over there. Like you can see, it's this is what I said, helicoidal architecture. So it's actually kind of like fibers. I think the picture on the picture on the. So this one I think is a bit more clear. Basically, what you have is layers that consist of fibers, but at every layers the fiber orientation change, and a lot of people have studied that this is actually the structure that creates that very high impact property. So I'm not saying that I didn't do that study. Actually, Miseres, that paper was among the first paper that reported that the particular 3D architecture was the one responsible for the very high impact strength. So what we do is just that we are we are taking this as a bio inspiration. Obviously, that kind of structure without additive manufacturing, that is without the ability to actually lay down one fiber layer at a time, it's not possible. I mean, if you just use conventional manufacturing, there is no way you can create that kind of structure. But now we have the tool in our hand that we can mimic we can create something that mimic what we have in nature. So in this talk, I will demonstrate about the result that we have. This is actually the result that that my team worked on maybe about 3-4 years ago when I was in Singapore, University of Technology and Design. That was the time I was in collaboration with MIT. The machine that we are using is actually nothing fancy. It's not even, I mean, the cost is probably just $50K US. It's not very, it's electrospinning. And electrospinning is actually has been around for 50 years maybe, even probably more. But we call it electrospinning based additive manufacturing simply because if it is so far with additive manufacturing, well, with electrospinning is nothing but you have your polymer in liquid form in the syringe, and then well, you push the syringe so that the liquid get out, and then you set up the electrical field here, and because of the electrical field, it stretches the liquid polymer, and based on how much electrical field you set up, you can create like a fiber dimension that is very small, even nanometer scale. But electrospinning as is not additive manufacturing because they just have with the electrical field, we can spit down the fibers, but those fibers are random. And in that sense, it's not additive manufacturing. It's just random. It spits out something, and then it will just create some sort of like, basically like a wool that a yarn that your cat has played with it. Like it's a intertwined ball of yarn. So, so in that case, then it's just like what is basically shown here is random. So about 5 years ago, we actually customized this equipment with a certain modification. So first, we have basically the idea that if this process is to be made additive manufacturing, we have to be able to control the fiber one at a time at exactly the right place, at exactly some XY coordinate in the sample. All right, so that's how to make it additive manufacturing. Otherwise, if it is just random, if there is no ability to control, it's not additive manufacturing. So then what we do is a couple of things, but the first thing is that instead of just this is just a platform. It's we put an XY stage, so that way we can actually control the movement of the XY stage with pretty high resolution. And then secondly, we are trying to stretch the electrical field is already stretching it vertically. So then if we are stretching it horizontally, so if we put this parallel plate here, and we also apply some electrical field, then we are again stretching it in the horizontal direction. So a couple of things that we did that allow us to actually lay down fiber one at a time, one next to each other, and have a control of changing the direction every layer. So that way we actually can realize, I'm coming back to this structure. So because this structure, we have to be able to put one fiber at a time and put the next fiber next to it with uniformity, controlled place, and controlled diameter. And then in the next layer, we need to be able to change the direction a little bit, rotate it a little bit, and then lay down again the fiber one by one. So only with the additive manufacturing methodology that we can do that. So that's basically what we did. So the next few slides, I will not go too much detail, but basically we are able to fabricate that. So this result shows one particular thing that we reported, I think this is back in 2020. Oh, by the way, Dr. Rahul Sahai is actually in the audience. This is my collaboration with Dr. Rahul Sahai in Singapore University of Technology and Design. This is one, this particular thing is actually, as you can see, you can see the artifact of like plus minus 45 degree with 0, 90. So that's basically the orientation of the fiber for every layer. You can also go zoom it down, then you can see the detail. So you see the fiber here, and that fiber, as you can see, there is like 0, 45, 90, 180. If you look at the legend here, it is 100 micron. So this fiber is actually maybe about 20 micron. It's pretty small, and this is actually getting towards what is in the mantis shrimp dactyl club. The fibers there is actually also nanoscale, close 100 nanometer scale. So we are trying to get the fibers smaller and smaller and smaller so that we can mimic exactly the structure, the 3D architecture that is shown in the mantis shrimp dactyl club. All right, so obviously I think it is not difficult to imagine why, if we have layers of materials consisting of fiber and then they keep changing direction, I think it's not difficult to imagine that if we have some crack in one layer, for example, then that crack want to propagate, but when it propagates, it sees like the next layer has different orientation. So then the crack will be stuck in that layer. In that case, then that's why this structure will lead to like higher fracture toughness. So that's basically what we are doing here. We did a lot of tests that it is enhancing fracture at the nanoscales. And in fact, one of the, not only fracture toughness, it's actually impact resistance. So we did a bit of a study with steel ball. So we have this ball, and then we have like a piece of our sample below. I think I have the, yeah. So as you know, I'm also working on solar PV. So what you see here is actually silicon solar cell, the blue color. So this is silicon solar cell, but on the top we put that material. It's transparent. So we put that material, and then we drop the steel ball, and we will, you put like, let's say 10 centimeter, and then you drop it. It doesn't break the silicon solar cell, and then you increase the height to become, let's say 11 centimeter, you drop it, it still doesn't break, you keep increasing it until it breaks. At some point it will break, right? So, that's what we did, and then, this is simply because the sample that we produce using our technique is actually rather small. It's like 1 or maybe 2 centimeter by 2 centimeter. Even those pieces of 2 centimeter by 2 centimeter will take like days to produce. So we are not able to do like conventional impact testing. I think people who are in mechanical engineering know the pendulum swing thing that we use for impact testing. It's not possible because it's too large. So then what we do is this steel ball drop test. We published this actually earlier in 2021. So we show that, I think we have a bit more. So I think, okay. So this is actually, we have a lot more data set actually showing this, but this is actually sort of giving us the idea. So if we have, let's say, bare silicon cell and then silicon cell with EVA. EVA is actually just normal polymer. There is no 3D architecture. It's just normal polymer. And then we have our material, HASSC 15 and HASSC 45. That just means that the 15 is the rotational angle. So we have layer with fiber that is keep rotating at 15 degree, after 15 degree, after 15 degree. So what we show here is that if it is just bare silicon, it will, at 25.39, it will break. So if we drop the steel ball, it's the same steel ball, then it will break. So if we put some kind of solid or just polymer with additive architecture, it will double it. So at about 48.97, so it's much higher, only then it will break the solar cells. But then if we put our material, which is 15 degree rotation or 45 degree rotation, it is even higher. So it's 70 centimeter and 82 centimeters. So that gives you an indication that the material can absorb a lot of impact energy. And thus it is actually protecting the fragile silicon solar cells that is under it. So that's basically the result that we reported in this paper. I think I've shown the paper here in polymers. And that's an example of how the additive manufacturing methodology allow us to have this extraordinary property, but also with now that we are able to control, for example, the diameter of the fibers and even the rotational angle, how much layer that we built, and then what is the interface between those layers, for example. So all those things will allow us to create almost like basically what we call tune. So we can tune the impact, energy, absorption, performance that the material will have. So obviously, we haven't been able to do that because we haven't been able to produce one fiber at a time with control. Only now that we can do that, and because of that, we can create, we can customize what will be the material or the mechanical properties, the fatigue properties, the impact properties of the material that you are designing. And that's, for material scientists, that's been our holy grail. Well, as I said, I'm a mechanical engineering major during my undergrad, but after my master's and my PhD, I became a material scientist. But still, a lot of my materials are basically things that are used in mechanical engineering system. And yeah, as I said, the holy grail for me is that, well, if I can play a little bit like God, basically creating the material and customize it according to what I want this material to have certain properties. And we are now a step towards that because of additive manufacturing. All right, this is just a little bit more study which we published a bit later in 2022. We did a little bit of modeling of basically what I described earlier about the steel ball test, steel ball drop test. And here, I think this is the layup of 0, 90, 180. So it's basically, it's an orthogonal kind of layup of fibers, layers with fibers. And as you can see, it will create some sort of like orthogonal. It's basically mostly just X, Y axis, right? And what happens? This is finite element modeling. Nothing fancy. There is no crystal plasticity. It's just finite element modeling. This is the layup of. Oh, this is still 90, 180. This one, if you put the layup of 0, 45, 90, 135, 180, so it's like every 45 degree rotation. Obviously then it will create like a bit more of like not XY, but a little bit more complicated kind of pattern. So this is the 15-degree rotation. So the idea is just that just like our experiment, we have like something brittle like silicon solar cell. We have the material that has 3D architecture, and then we drop the steel ball, and we want to see what happens in terms of stress distribution. What you see here is the stress distribution after that ball hit the material. All right. So, but what is really important here is, well, obviously, if you just compare between this and let's say this. Okay, it's a bit long, but it's basically you start seeing that rather quite distributed manner. But if you have 0.45, all right, so if you have 0.45, you only have very simple pattern of XY. But if you have 0.45, 90, 135, you start distribute it more evenly. And if you have 15, 30, 45, you distribute it even more. So what happens is stress is not concentrated. Stress will be distributed more and more evenly. And because of that, it is more effective to absorb impact, to provide the performance of impact absorption. And this is actually also something that is clear from this. So you, as you can see, the first one is 0.90. This is basically with stress with respect to time. So, and 0 is the point of when the ball hit the material. So the material will have some lag, and then at some point the stress will start, the material will start feeling the stress. It will be maximum, and then at some point it will be absorbed, and then it will be distributed, and then it will go to 0 again. But for 0.90, it will take this material, let's say 150 millisecond. So the ball drop, the material will be stressed a little bit, but then it goes back to normal. That will take 150 milliseconds. But if we have 0.45, you see that the pattern is similar, but this point, for example, is 100. Is about like less than 100 point. Or if we take this second point, this one is almost 130. This one is less than 100. So that way, then you know that the 0.45 layup is more effective in distributing the stress more quickly, and that's what lead to the extraordinary or enhanced impact properties of the material. What else is it good for? Those few papers that I've published with Dr. Sahai is mostly just structural material, how we can create like very high impact material properties. But this 3D architecture, this ability to create any, like basically build the material almost one building block at a time. That's the whole. That's what material scientists always want, right? I mean, like we create it like so that we can actually customize the mechanical properties. But in one of the other projects that I'm working on, so we are using the same principle, which is how we can lay down one fiber at a time, and we create the kind of 3D architecture that we like. For example, this lattice structure. So we use it now for next generation battery. So I think Professor Satrio has mentioned a little bit about battery and how additive manufacturing will actually revolutionize battery technology. This is one of them. I'm not going to talk about this particular work, but I think my student Lacey will probably give a bit of about that work a little bit more. Please attend the last session So if you want to know, Lacy can share a little bit more. But the idea is just that if you want to have 3D lattice, and that 3D lattice will actually lead to enhancement in the properties, now it's possible. Because before it's not yet possible to create like one and to create and control fiber at such a small scale and creating like a controllable 3D structure. Well, for this battery, one of the problem with the current battery is that when you have to charge it, well, one car, for example, it will still take like too long, because compared to fuel or gasoline car, you go to Pertamina, to gas station. Well, if you don't need to queue, that is, then it's just like 3 minutes. Your mobile, your car will be ready again to go another 500 kilometers, right? For electric car, it's not like that. Yeah, you have to be there. You actually have to charge it for like half an hour at least, if not 1 hour, right? I mean, it's so that's a problem. That means charging kinetics or the charging rate is still now very low. Well, charging rate is related to what happened inside. So if we can create, for example, the anode, where when we are charging, the lithium ion come from cathode to anode. So if the anode can be absorbed much more quickly because it's actually a 3D lattice, not a solid material, then obviously the charging kinetics will improve. So this is again what I said about things that are enabled by additive manufacturing that will create functionality or property that hasn't existed before, which is using a 3D lattice structure. About 3D lattice, I think if you watch Brody Miller's presentation yesterday, we are doing quite a bit about 3D lattice and what extraordinary performance in terms of mechanical properties or other properties like battery that it can do. All right, so I think that's all I have. So in conclusion, with additive manufacturing, now it is it is possible now to create 3D architectures, and these 3D architectures may lead to extraordinary properties or even functionality that hasn't existed before, and and we've shown it in one particular example, but obviously this is going to revolutionize the way we use materials, the way we create materials. And with that, that's the sponsor at the time. That's I acknowledge their support, and I'll be happy to answer some questions if you are saying. Thank you.
Right, thank you very much, Prof. Budiman. Is there any question from the floor at the room here? Or maybe from the Zoom? Is there anybody watching on the Zoom?
By the way, this was my group back in 2019 in Singapore.
Okay.
And that was me probably about 10 kilograms ago.
It seems there's no question from the floor and the Zoom. I have one quick question, Pari.
All right.
How far are we from achieving a very fast charging battery according to your proposed design?
Very good question, actually. We are, Lacy probably can answer this question better, but we haven't done the cell test.
All right.
But right now, Prof. Evi Kartini is also here. We are collaborating. We are producing the anode with the 3D architecture, and then we integrate it into a cell, and we have to test it. But the 3D architectures in some form we have produced. And with 3D architectures, I mean, it's obviously when you have that much surface, the 3D lattice just means we have a lot more surface that are open, and the lithium can just come and then be absorbed by the surface. So when you have that much of a surface compared to the area, then the absorption rate will be higher. I mean, that's just simple physics. So if we have this 3D lattice, it's a matter of just fabricating it. But if it is there, if the structure is there, it's going to lead to higher charging rate.
All right, excellent. Thank you. Thank you very much.
All right, thank you.
Let's give a big applause to Professor Budiman. We still have a couple more presentations, so bear with us before you take your lunch. I hope the next one is quite quick. The presentation will be from our distinguished Master of Ceremony so far, Ibu Dr. Nimade Dwidiani, and the title is The Prediction of Photoactive Semiconductor Potential of Bioactivated Rice Husk Ash Using Analytical Method. I check her Google Scholar. Actually, she's been actively researching and working on the carbon active and biomass energy. Please, Dr. Dwidiani. Time is yours.
Good afternoon. I will give you a short one, so you will be happy because we will have a short break. This is actually the preliminary stage of my research in collaboration with another university. So basically what we want to have is photocatalyst, bio-based, with bioactivated, because we will use it for crab hatchery. So the photocatalyst will be used in a mangrove area, because now mangrove is big, is trending, big. We can convert it with carbon, we can sell it. I mean, developing countries can sell their carbon by mangrove, and it will very expensive, but they come with a lot of risk as well. All right, next. Yeah, the collaborative project is a green hydrogen and crab hatchery. The roof will be made of solar, and then the electrolysis will be at the bottom, but we also will use this platform as an educational program, almost like a small hydrogen village. And at the bottom will be the crab hatchery. So the idea, because we will use a crab, the oxygen produced by the electrolysis will be given back to the water, so it will be good for the crab hatchery. And the photocatalyst will be enhancing the hydrogen production. Next. The collaboration, as you see, some from Singapore, United States, and Hong Kong. Also, we also have a Fab Valley in Jimbaran. So the outline is the introduction, material, method, result discussion, and conclusion. Next. The background is quite obvious. Green production, we try to utilize waste, and also because we have it abundantly in Indonesia. So I think that's the positive one. And then renewable energy, organic photovoltaic, sustainable. The activator is also very bio. Hopefully, so far it's already proven, low energy, low temperature production, and tunable band gap for electronic properties. I'm also working with supercapacitor previously using biomass. So I think that's quite in line with my research. And also alternative transistor or diode material. Next. The aim, predict potential of P-type semiconductor material from rice husk and activated by pineapple peel juice. So this is important. I don't want to compete with the food safety, so I'm just using the peel of the pineapple juice. The characteristic of the P-type semiconductor material, whose rice husk base and pineapple activator. Next. Material, as usual, rice husk, pineapple, and for the rinsing we use the ionized water. Next. The method is kind of mechanochemia, and using grinding the rice husk up to 200 mass, and then using high energy milling, and this is tailor-made, handmade, and using 100 million cycle. It is shakers with 5 millimeters diameters of steel ball, hardened one, of course, and then activated 100 degrees for 40 hours, for 4 hours, sorry. The 60 degree is related with the enzyme does not work anymore or broken by 70 degrees. So we are using 60 degrees, which is quite safe for the bromelain enzyme that available in the pineapple. Of course, rinse and separation. And the separation, we took the sunken material as well as the floating material. If we can get the sunken, or even possible to have just the crude one, while we go to the higher degree using the floating one. That's the idea. But if the floating one have better characterization, then of course we will take the characterization. The high energy milling is also very interesting, because I just found out recently that Pajajaran, so I think further collaboration will be improved there. Pajajaran also have high energy milling, which is quite important and even faster, because they're not using steel as the ball. Next. So from both sides, I'm using the semiconductor characterization as well as the photosensitive of the material. For the semiconductive, already finished, but for the photoreactive is still in progress also, because the limited of the facility and the capability of the test equipment available. So I have to work around that challenge in my research. So with the analytical method, we found out that the photosensitive of the material is quite good. Thank you. Next. So using the SAM, we got from the rice husk, which is not being bioactivated yet, compared to the sunken material, so the SCNM, and the floating one, which is surely finer than the sunken one. We see that the big glomerular on the rice husk and the hierarchical morphologies of the material, both on the sunken as well as the floating one, in which the some of the floating one has a smaller size. Next. Using the ADX, it's shown that the semiconducting properties of the material, rice husk not so much. Next. The sunken material as well as the floating has quite promising in terms of the copper oxide content as well as the silicon content. The copper oxide content is very important in terms of their semiconducting properties, as in the rice husk, the comparison between the carbon and silicon is 10/3. And the sunken material is 5/9 with additional ferrous and aluminum in that material, while in the floating material, it's 9/4 with additional copper in the material. The copper oxide has shown in all the materials, showing that a very good semiconducting properties of the material. Next. So still ADX. Next. The content of the silicon cannot be tested yet, as the FTIR showing capability is just until up to 4,000, while the silicon is up to 15,000. Next. For the UV phase result, showing that the peak is around 200, so it's not much different, but quite significant, showing that the product is very in infrared area for 800 to 200 for silicon, but the copper oxide is between 200 to 400. Next. For the analytical result, the showing of the whole carrier, the concentration between the three material, the big difference between the rice husk, which is the raw material basically, compared with the already activated by pineapple, the sunken and the floating showing not much difference in the whole concentration, and the band gap energy actually quite promising. It seems that the sunken one has the band gap energy lowest. So we still have, it means that we still have to use, could be both, depend on what is the requirement or what the purpose. Next. So electron hole pair compared with the mass content of here, the electron hole pair is lowest on the rhesus S, and the mass of the copper oxide content is the lowest on the rhesus S. Next. So the conclusion, it seems that very promising, the energy carried by the hole can be predicted using analytical method. But I need still to carry it out with the photoelectric test to see the performance of the silicon, to show more of the photosensitive characteristic of the material. And it seems that the sunken one, which is I don't have to choose the finer material to extract copper oxide due to its lower band gap energy and highest hole on the highest electron pair as well, and producing more copper oxide. So it seems that I don't have to go for the finer material, got the kind of more crude diameters, but it get the semiconductor photocatalytic characteristic of the material. Next, that will be all. Thank you. Give the short one.
Thanks very much, Dr. Dwi. Maybe a couple of questions. Is there any question from the floor? Maybe Pak Arif, you have a question? Okay. I'll check on the Zoom whether they have a question. Right, it seems there's no question. Budwi, thanks very much for the presentation.
Thank you.
Hope the research goes well.
Thank you.
Thank you
Thanks
very
so
much.
much. I need that.
The next speaker. Oh. All right. Okay, we come to the last speaker of this session. Sorry. The second last of the speaker for this session. Please welcome Dr. Rahul Sahai. His title is Constrained and Unconstrained Interface Rotation in Nanoscale Multi-Layer CU and NB Materials from Singapore University of Design and Technology. Please, Dr. Rahul.
Thank you for the introduction and inviting me to this conference. So I will be explaining constrained and non-constrained interfacial plasticity in this ARB nanolaminate. Next slide. So basically, we have been designing nanolaminates for a while now, and it is basically based, it has some clues to the nature. Basically, we take some clues from the nature. After explaining about nanolaminates, I'm going to explain two techniques to study the interfacial plasticity of the nanolaminates, then compare them. Then later on, because it is a AM conference, I'm going to little bit talk about how interfacial properties are relevant for 3D printing. Next slide. So for me, material science is all about crack. So basically what we are doing, we are trying to avoid cracks. Anywhere we'll see. So you see a ship here. This is a Liberty ship. Basically it was built by USA for UK to fight in Second World War. But because it was made of cast iron, and when it reached into the sub-zero temperature seawater of UK, it just cracked. So metal is strong enough, but still it has a lot of issues. Now, if we go through one of the examples which I really like is bone. So how they are managing bones? How they are managing that? Because nature itself is trying to avoid propagation of cracks. So how bone works? So to start with, we don't have very strong material. So our bones are made up of collagen, which is a polymer in nature, which is soft. And the second material is calcium compound, which is brittle in nature. So nature don't have very strong material to start with. So it have some calcium compound and some polymers. So if your bone is only made up of collagen, it is soft in nature, and then your bone is going to bend. This is the case usually happen in the old age. When people lose calcium over time, their bones start to bend. Their legs bones start to bend because of the weight on the top part of the body. If your bone is only made up of calcium compound, it is brittle in nature, any crack will just propagate through it like it propagates through Liberty. So how the bone works, it has collagen fibers which are mineralized inside and outside the fibers. So when a crack propagates through the bone, it will see hard, soft structure. So let's say first the crack goes to the hard material, calcium material, and it is able to break it. Then it will go to the soft material where the energy is dissipated. Again, it goes to the hard material, again it goes to the soft material. In the process, the energy is dissipated. That's how the bone is able to survive. Same thing, this mantis shrimp, Prof. Arif was already explained. The same thing we are doing in copper niobium nanolaminate. It is the same thing. It is hard soft material to avoid the flow of crack to the layers. Please go to the next slide. So this is a very simple process of producing nanolaminate, but it is quite tricky. Usually what you do, you start with millimeter layer copper and niobium, and then you do some surface treatment, and then they squeeze them out to the rollers. It is something like making sugarcane juice. So you have a sugarcane, you roll out through the rollers, and then again you fold the sugarcane, then again you roll out. So here the juice is the plasticity. So you keep on rolling it, and it plastically deforms, and the grain size increase along the rolling direction. So because you are rolling in a certain direction, the properties in the rolling direction and properties in the transverse direction are going to be different. So because of the rolling is done in a certain direction, you will generate an isotopy in the material. That's what we are trying to study here. So what we assume that in the rolling direction, the plastic deformation has been so much that the layers are so close to intermingled each other, shearing is not possible. But in the transverse direction, because there is no rolling, the material can move in the transverse direction. Material can easily move in the transverse direction compared to in the rolling direction. These interfacial properties are also good for 3D printing, because in 3D printing also what you are trying to do, you are trying to print in the single direction. So the properties in the printing direction and properties transferred to the printing direction are going to be different. Next slide. So we have a very good instrument and in our lab in STD, courtesy to Prof. Arif when he was there. So this is a in-situ pico indenter. So what you can do different kind of experiments. So our sample is here. Then we have a indent. So you can indent your sample. So you can see here, this is the force. The force is coming from here. And this is your sample here. So this is our micro beam with a notch, and we are indenting. The force is this force. So this is one of the experiments which is basically what we are trying to do. We have a notch, so we are controlling the flow of the crack through the beam. If we don't have a notch, the beam can crack at the ends too, but we don't want that. So we are controlling the flow of the crack. That's why we have a notch in the beam. Second is micropillar compression. So we know that when we apply a vertical force, the maximum resolved shear stress will be highest at 45 degrees. So for this micropillar, the maximum resolved shear stress will be higher at this 45 degree. That's why we have created a pillar in such a way that the interface is at 45 degree. So we are trying for the interface to slide. So design is such that we want it to slide. So basically, as we want to study interfacial properties, we want to make sure that interface is active. Next slide. So I will discuss about in situ micropillar compression. Next slide. So as we have seen that in the first A and B figure, you can see that because the pillar basically this pillar is made along the RD direction, rolling direction. So it moves, but because of the constraint here, it rotates in the RD, in the TD direction, because it is easier to rotate it in the TD direction. Similarly, in the TD direction, you will see a interface generated. Basically, you will see a copper layer there, small copper layer, with the interface has moved at both the direction. That's why in the case of TD, the shear resolved stress is higher and it is increasing with the loading. Whereas in RD, because the interface has been blocked and it rotated in TD, the shear resolved stress is very low. So here we have basically analyzed that interface moves along TD very easily compared to RD. Next slide. So now I will discuss about microbeam bending experiments. Next slide. So this is quite an involved process. Basically, we use F5V to create microbeams with a notch. You can see the notch there. And you can somehow see the layers also there. The notch is to control the flow of crack. Next slide. So this is a video. So basically, you are loading at the notch. This will play. So when you load the beam, you will see that there is a notch widening. Basically, this beam is along TD direction, and we assume that there will be a interfacial sliding, which you can see here. Because what is happening here, because in this 16 nanometers beam, this is 16 nanometer beam, the layer thickness are all 16 nanometers. So basically, we have so much we have done so much rolling that bulk plasticity is more or less gone. Because the layer thickness was 1 mm, it was reduced to 16 nanometers. So bulk plasticity is more or less gone. The plasticity which is left is at the interface. So what happens when you apply loading to it, because 16 nanometers, there is no, dislocation will not come together, and there will be no crack propagation. The dislocation will be deposited at the interface, and which will give you interfacial plasticity here. Next video, next. So this is the final image. Basically, we show that you reach to a certain stress, then the notch at the same basically stress, the notch widening take place, and later on the crack goes through and your beam breaks. But in this experiment, you have already seen there is enough notch widening to show that the interface moves along TD. Next slide. So we have shown that interface moves along TD. What about if interface moves along RD? So it is possible to do that too. usually what we do, we give offset loading. So if we give an offset loading, so you can see here, instead of applying load at the notch, we are applying load at offset distance. So if we move this load to the notch tip, so one load is here and the corresponding load is here. So what you will have a load plus a movement. So you will have a load at the notch tip plus a movement which is squeezing the notch. So it is not allowing the plastic deformation to take place along the TD direction. It is squeezing the notch. So when you squeeze the notch in the TD direction, the notch is the shear which is supposed to be in TD direction is going to take place along RD. So next slide. Yeah, this is a video. So you can see here the notch widening is not great compared to the first image where the loading was at the notch tip. Second video, so basically we break the beam. So this is the first loading, then second loading. We are trying to break the whole beam away. This is a video. So you can see here the interfacial plasticity is not high. The beam has already started to crack and breaks away. But you will realize that because there is a constraint for the notch widening in TD direction, there will be a shear in the RD. Next slide. So here you can see that the load in this case is increasing because there is notch widening, but there is enough load which is applied for the layers to slip towards the RD. Next slide. So this is a comparison. Next slide. So here you can see that load applied at the notch, you see a notch widening and the breaking of the beam. But in case of when the load is applied at offset, the load keeps increasing and the beam is not, notch is not widened, but the layers move along the RD direction. Next slide. So here you can see that, so this is the broken beam and you can see that the layers have moved along the RD direction. So the idea is that any isotopic material, when you apply enough load, the interface is going to slide. There will be interfacial plasticity in the RD or TD direction. Both directions are possible. It's just the amount of load you apply. So this scenario goes well with the 3D printing also. Next slide. So interfacial plasticity is relevant to 3D printing. So here also, if you have layers, let's say the first case, so you have layers into the plane of the board, and you fly a load, there will be a interface will break up. So usually while designing a 3D printed material in which you are using fiber, here this is the fiber structure, there is no matrix. You have to make sure that loading is done in such a way that the horizontal forces so in the second case, the load, when you apply the load in this case, the load is covered by all the fibers. Here it is not, it is just by certain interface only. So whichever is the poorer interface or poor adhesive strength, the interface is going to break down. So we have to design 3D printed material in such a way the fiber structure has to cover all the possible forces applied to the system. Second case is this. Basically, people have tried to use fine layer structures because they think that if you have the fine layers, you can get a higher precision. But you can see there, if you have fine layer structure, you will have a numerous amount of interfaces compared to the coarse layer structure. So if you have more interfaces, there are more chances for the interface to break. So the number of interfaces increases, the high chance the things are going to break somewhere or another. So the easiest solution is that you mineralize it. The same way the bone has done it. In bone you have collagen fibers and they are mineralized with calcium compound. So that interfacial properties didn't come into play. So that's one answer. But if you are making some structure totally with fibers, you have to take care of our interfacial properties too there. Next slide. Oh, so I forgot to add the important slide here. So this work was done in collaboration with Professor Arif when he was in SUTD. So we got very good funding. We got funding from NRF, and we also got funding from Japan. Professor is there. So we have been working on this for a while now, and hope we will be getting good results in this area. So we have a very good machine in our institute, this Institute Pico Indenter. So if somebody has samples, we want to see how their samples behave, microbeams or microplayer behaves. They can contact us, we can do that for them. Thank you for your time, thank you.
Thanks very much, Dr. Rahul. Please stay a while, maybe there's a question from the audience. Okay.
I'm loud enough. So I think it's very similar theme with what I asked Mark John earlier. Like defects is not necessarily something that actually lead to the weakness of the whole material, because you are saying here by engineering the interface, maybe through 3D printing, that you can get a favorable properties. Maybe you can elaborate on that, Professor, Dr. Sahai.
So interface is, in this case, is very important, because usually they are ways of doing it. When usually how they do 3D printing is that most of the time they have a resin, they have a matrix material, they have fibers, and they have a matrix material which take care of all these things. Matrix material is going to attach to the fibers, and then you have it is same build like. So we are following the nature to the point, to the brim. So in the way the bones are made, the same way they are doing. They have fibers, and because bones, the collagen is a polymer in nature, so they are also using polymeric fibers, and then he's mineralizing the whole thing up. But if you want only fibrous structure, only fibrous structures, interface adhesion has to be will play a very important role there. So first thing is, while you design, you make sure that you don't have structures where interface is easily to tear out. Second, you can do heat treatment after the sample is prepared. So basically, you can improve the adhesion. And when we made this copper niobium laminates are prepared in Los Alamos, even though those guys do interfacial processing to make sure that the layer adheres to each other. So depending on the material system, whatever you are using, you have to take care of the interfacial properties and make sure that they work well for your system.
Right, thanks very much, Dr. Rahul. If there's no more question, we can move to the last. Thanks very much. We have moved to the last. Sorry, we have a big applause first. Sorry. Then we move to the last presenter, Dr. Dr. Andi Ardi Amadia, with the title of Zirconia as Oxide Dispersion Strengthened on the Iconal 718 Fabricated by Selective Laser Melting. Sorry, it's actually miss. All right, that's good now.
Ini yang terbaru atau baru di-download atau dari pagi? Can I start? Okay, good afternoon everyone. It's an honor that I can stand here to present about my topic today, zirconia as oxide dispersion strengthened on Inconel 718, fabricated by selective laser melting, or we can say it another is powder
diffuse. And let me introduce, my name is Andi Armaida, and another is my supervisor, Chil Pejang, that actually today our professor cannot come to because something happened in Taiwan. Next. Okay, this is my outline. First is introduction, second is material and method, third is result and discussion, and for the last, conclusion and the future work. Next. Here our professor, our supervisor. To the committee, we said sorry because our professor cannot come today, cannot come to the Bali. Professor Jiang, our professor, just finished the education in the NTUST, and now our lab is focused about additive manufacturing, and for me, I'm focusing on selective laser melting, and for the material is Inconel. Properties, first for the corrosion resistant in high temperature, and the second is because the Inconel has a strong mechanical properties. So we try to build the Inconel, and because Inconel can fabricate by SLM, we try to change, make a new topic at the zirconia, become composite of Inconel and zirconia. The aim, we try to make a new, not new, we try to change the mechanical properties. For this is the hardness by add some of the zirconia and Inconel. As we know, Inconel, when they print by SLM, has some problem because the anisotropic. The first cannot homogeneous first, and the second different size. And because as we know, the selective laser melting always use laser print the material layer by layer, so the material will be reheat from the bottom until the top. It will be a problem for the Inconel 718 and can disturb the mechanical properties. So we, by edit the zirconia, we want to improve the mechanical properties, especially for the hardness. Next. To improve the mechanical properties, we can do for the change the printing parameter for the SLM, and then another for the heat treatment. As we know, in Inconel, if we want to improve the mechanical properties, we do for the heat treatment and edging, especially. And for the another, we can add the filler. So by add the filler, we do ODS, oxide dispersion strengthening. We add ceramic that contain oxide, and then by the ceramic, we try to make a rapid cooling when the printing process, and then we try to improve the hardness, thermal resistant, corrosion resistant. And because of that, in Taipei Tech, we try to print by SLM in Inconel 718 at the zirconia 1% and 2%. Next. Here's the material and methods. First, the materials, because we want to make the composite, the Inconel 718 as the matrix with the composition nickel base, more than 50%. And then the zirconia as the filler, we add the ferrous 1% and 2%. We did the 3D printing by Tongtai IMP 160, made in Taiwan. And then for the material testing, we do for the simple test like SEM, XRD, TGA, DTA, and micro hardness, because we just print the small material. So we try to do every material testing that can use for the small sample. In the picture, we can see that this is for the our machine. Actually, I take this from the Google, sorry, because the machine is a big, so I cannot take a picture, and our room is small, so not good. And for the parameter, we use for the laser power and scanning speed, layer thickness, head spacing, as in the slide. We use this parameter because before we already published about the optimum parameter for pure inconel by our machine. So that's why we use that parameter. And for the direction, 66.7 each layer. Direction can change every layer. And for the material, the sample, as we see, we can see, there are 3 types of the coupon. Another for XRD for the small, for the TGA, DTA, and then for the micro hardness is the biggest. Next. Here are the materials. Before we do the printing, we already do the SIM index, SEM index, and then it knows that for the inconel, nickel has more than 50%, and then another zirconia that contain oxygen and then zirconium. We did preparation for the powder to mix the powder inconel and zirconia become one. And here from the picture, as we know that zirconia still have a big size, bigger size than inconel. But when we want to print, we want to change the size of zirconia become smaller. So we did the ball milling without the ball. We just used the inconel to crush the zirconia, and it takes time more than 2 days. Next. Here, after the mixing process, that side, totally the spare is inconel, and for the zirconia, it becomes smaller into the, I can say that into the nanoscale, because very small, and then it sticky in the inconel surface. And after print, here for the magnification of 200 micrometers, from by at the zirconia 1% and 2% still has a defect, and the defect increased the zirconia, and it show when I use for the magnification of 30 micrometers, still have a bigger crack, actually for the 2%. So from this picture, I can tell that if we want to print the zirconia in inconel, by use the parameter processing of pure inconel is not enough. We have to try change the parameter so the defect can minimize. That's our homework for the our microstructure. Next. Here another test for the XRD. powder and after print I tried to do for the XRD test, and it show both of the powder and after print, the highest peak still in Cornell, gamma and gamma accent phase. About the zirconia phase, it's very weak, so cannot see clearly in the picture. It's around, it's at the 30 degree for the zirconia peak. As we know, it's too weak. And then after print, the peak change, but only for the plane direction. The phase still same, still gamma and gamma accent, and because we didn't use for the heat treatment, there is no phase like a gamma double accent or another phase. And from the XRD, it showed that there is no reaction between inconel and zirconia, so there is no another phase or new phase. Next. For TGA, we try to want to know what's the effect of the zirconia if we add in inconel. By the literature, normally inconel has oxidation, start to oxidation around 450 degrees of Celsius, but when we add the zirconia, it's around 700 degrees of Celsius, even for 1%, and little increase by 2%. Actually, I have been print for 10% and increase until 800 degrees of Celsius for the oxidation range. And for the hardness test, as we know before, the SEM result for 2% has a more defect, and it impact for the hardness. So for 1% become the highest, more higher than the heat treatment. The heat treatment only around 600, and by you added 1% of zirconia, the hardness, the micro hardness increased until 800 hardness figures. Next. And here for the conclusion, first, still have the defect, even for 1% and 2%. Normally, the defect is about because the parameter processing need to improve, like the porosity, like the crack. And then for the addition 1% and 2%, still present the gamma and gamma accent for the after printing. And for the TGA-DTA, can show that in Cornell by add the zirconia, the oxidation temperature increase from the normal. And for the highest hardness number, 1% can increase and significantly than the heat treatment double aging. Next. Here our future work. First, about the defect. Our homework is try to change the parameter, even the laser power of even the layer thickness and another about the parameter processing. We try to change it for the next research. And then because we just use for the simple characterization and mechanical properties, our homework to observe more the mechanical properties and characterization. We try to do like a tensile test and another mechanical testing to find out the effect of zirconia in inconel. I think that's all. Thank you very much.
Maybe
In Cornell?
Yeah, internal. What are the? Yeah, I think that's one of them.
No. Next.
What are the size of the? So those are the powders, not this one.
Oh. Before. Next. Yeah.
Yeah, this one. For example, let's say this one. So what are those are the powders, right? What are the size of them? Because I don't see any light anymore.
Yeah. That's
There, maybe my eyes cannot catch it. But
okay.
like this one, what is the average size here, and what is the average size here? Because your objective is you want to make it homogenized, right?
Yeah. Okay. That's homework from my professor too, because not yet to average it, but I try to cut some picture and to try to calculate for the inconel. The size start from the 10 micro until under 50 micrometers, and for the zirconia around 30 to 60 micrometers. From this picture, it's too bigger for the zirconia become filler, right? So we try to ball milling to crush.
Thank you. If there is no more question, then I think lunch is waiting for us. And thank you again. Let's thank again Ms. Maida.
Thank you.
Let's give another applause. Yeah, then we'll now it's time for lunch, and we'll get. I think we'll be back here. Well, the schedule was supposed to be 1:30, but I think we'll get back here at 2, which is half an hour from the schedule. All right, and we'll be broken into 2 sessions again after lunch. And if you are interested in 5A, it will be this half. 5B will be that half. I mean, just like yesterday. So 5A, the A is always the one with Zoom. Yeah. So if well, you actually you don't know which one may present with Zoom, but I know 5A, Professor Avinas will and Professor Ariwibo will be presenting with Zoom. So it will be this Zoom. Yeah. Okay. So let's have lunch.
Ini untuk sertifnya gimana?
Sekarang aja kasih, langsung kasih. Siapa tuh yang mau dikasih? Oh, saya.
Atas nama ibu.
Oke, satunya?
Mr. Rahul.
Ibu kasih dong.
Udah nggak ada di ruangan.
Kasih nanti di lunch.
Iya.
Tahu kan? Oke.
Solo ke Pakintit. Iya lu. Mohon nage pani jenik jali angnya sing lah ben.
Emang dia.
Nggih. Kan memisi lah disik. Iko pemisi lah.
Tes tes cek sound 1 2 tes 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 1 2 tes 1 2 tes 1 2 tes 1 2 tes tes 1 2 tes 1 1 2 tes 1 1 2 1 2 tes 1 1 2 keras lah keras apa nih keras nih tes 1 2 tes 1 2 cek tes 1 2 tes 1 2 keras tes 1 2 tes 1 2 tes 1 2 tes 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 1 tes 1 2 tes 1 tes 1 2 tes 1 2 tes tes 1
Recording stopped. Check, check. Nanti kalau saya ngomong ke sini kedengaran ya. Oke. Hello. Hello, Prof.
Yes.
Baji and Prof. Ari. Good afternoon.
Yes, I'm here.
Hi, Prof. Zaki Saldi speaking. I'm the chair of this session. Prof. Baji and Prof. Ari Wibowo. Apologies for the long delay. We shall begin really soon. The participants are entering the room right now.
Sure, no problem.
Okay.
Sounds good. Okay.
Selamat siang, Pak Ari.
Selamat siang.
Okay, maybe we shall begin this session soon. Good afternoon, everyone. Welcome back. Now we are in session 5A, and we are behind schedule, so hopefully we can move on with the presentations in this session as soon as possible. As scheduled, the first presenter is Professor Avinash Baji from La Trobe University, Australia. Welcome, Prof. Baji. Thank you for joining us through Zoom. I will short a very short bio of Prof. Baji. Professor Avinash Baji obtained his master's degree from and also his PhD from University of Akron. His PhD research focused on the development of high toughness and high strength bioactive composites. After completing his PhD, he joined the research group at the Center for Advanced Material Technology at the University of Sydney as a postdoctoral fellow. Following that, he was an assistant professor at SUTD from 2013 to 2018, and at the moment he's a senior lecturer at La Trobe University and is working on on establishing the bio-inspired materials research. He has authored and co-authored over 70 journal articles with papers also in proceedings and referred abstracts. Thank you, Professor Baji. Professor Baji will present his work on electrospinning-based additive manufacturing in advanced functional and piezoelectric materials. Without further ado, Professor Baji, please. Thank you.
Thank you. Thanks for the introduction. And again, I'll, just like the other speaker, I'll also apologize for not being there physically, but hopefully you'll find this talk interesting enough. And I'll try to give a brief talk so we can catch up on the next presentations. So I'm just going to give a very quick introduction and also introduce the kind of work that we did in our lab. I'm going to focus mostly on two different types of studies that were done. One is on using electrospinning for producing piezoelectric fibers, PVDF fibers. Another one is on using electrospinning again for producing multiferroic fibers. And then lastly, I'll conclude the talk by giving some applications of these fibers. So first is just to give a quick introduction on what piezoelectricity is. Piezoelectricity is, it's typically a ceramic material. When you apply certain voltage to it, it deforms, and vice versa. When you apply strain to it, mechanical deformation to it, then it produces voltage. Very simple, but this has got tremendous applications. You can use these materials for sensor applications. You can use this for energy harvesting applications. Especially very recently, these kind of piezoelectric materials, they are being used to harvest mechanical energy. People are started using these materials in the sole of your feet, on the backpack. These straps of your backpack have been replaced with piezoelectric materials. And every time you move, it generates certain amount of voltage. this voltage can be harvested and then it can be used to power small devices such as your cell phones. Now, there are many piezoelectric materials that exist. Mostly piezoelectric materials are ceramic based, such as barium titanate, PZT, bismuth ferrite, etc. There are also polymeric piezoelectric materials such as PVDF. PVDF has got some piezoelectricity, but it is lesser compared to the ceramic materials. So the response of this polymer is lesser, but however, what we've seen is that its response, piezoelectric response, can be enhanced when you produce these materials in the nano range, nano typically less than 200 nanometer in diameter. So with that motivation, we have started using electrospinning. Very brief introduction about the polymer itself. This is the backbone of the polymer chain, PVDF. Now, PVDF has got fluorine atoms that are negatively charged and hydroxyl atoms. Typically, PVDF is formed in alpha phase. Alpha phase is non-ferroelectric. It's non-ferroelectric because your fluorine atoms point in one direction and your hydroxyl atoms point in the other direction. So it cancels out. However, PVDF can also be formed in beta phase, where your fluorine atoms can be aligned in all these fluorine atoms can be aligned. And when they're aligned, then you do see a effect, piezoelectric effect. Electrospinning is useful for this because electrospinning mechanically stretches this material. And when you're mechanically stretching this material, it tends to reorient these atoms and it orients them along one particular direction. So what we have done, our study was on investigating the effect of fiber size on the piezoelectric behavior. We produced various different diameters of fibers, and we show that when fibers are in nano range, then its piezo response is much higher. And the reason is very simple. Piezo response is higher because thinner fibers, they tend to elongate to a greater extent. And during that elongation stage, it tends to reorient the atoms. So the method that we used is we produce these fibers in the yarn kind of format or yarn kind of structures. We dissolve this PVDF in a solvent, electrospun it on the surface of a water surface, and then pull these fibers with the help of a mechanical roller. And when you roll the fibers, then the fibers also tend to get aligned, something like this. We saw that the fibers were highly aligned. The diameter of the fibers were around 70 to 400 nanometers in range. Following this, we started to investigate its crystal structure. We found that when the fibers are in nano range, 70 nanometers or so, this peak was much higher. This peak is attributed to the beta crystal, whereas the other peaks are attributed to some alpha crystals, such as this one and this one. So we saw that as you reduce the size of the fiber, the intensity of this peak starts to increase, which is a clear indication that the beta crystal content in the material has increased. We also did FTIR. We saw that the FTIR spectra had bands associated to both alpha and beta crystals. However, we took two main characteristic peaks that are associated with beta crystals, and we used this formula to determine the fraction of beta content in the fibers. This represents the beta crystal wave number, and this represents the alpha crystal. It's interesting that all our fibers had only two different crystals. We didn't have any gamma-based crystals. Gamma is also piezoelectric, but in our case, we only saw two different crystals, which made our life a lot more easier. And we found that the fraction of beta crystals were higher for fibers that were in the smaller range. So 70 nanometer diameter had higher content of beta. Following this, we investigated its piezo response. Piezo response we investigated using using piezo force microscopy. It's something very similar to AFM. All it does is it also applies voltage and determines the phase as well as the response, the strain response. So all our samples showed this kind of behavior, very interesting behavior, where it shows a clear 180-degree phase shift when the voltage is reversed, when the applied voltage is reversed. And this is a clear indication, this kind of shape is a clear indication of a piezoelectric material. We also saw this response, the butterfly loops, as it's called. This is when you apply a voltage, you're measuring the change in the amplitude, or in the strain rather. So we saw that when the voltage is reversed, the strain also reverses. At certain voltage, at negative voltage, the strain is positive and then it switches. So this is again an indication of a piezo response. Very quick summary on this, the first part of the study. We saw that 70 nanometer diameter fibers had the best response compared to other ones, and which agrees with our hypothesis that as the size of the fiber decreases, the beta content increases, and if the beta content increases, then its piezo response has to be higher. All right, I'll move to the next one. This one is on multiferroic fibers. Multiferroic fibers are ones that can show two different responses. These fibers or these materials are ferroelectric and ferromagnetic. And again, they have a lot of different applications. They can be used in sensors, they can be used in memory devices, etc. Very few materials currently exist. Bismuth ferrite is one of those materials that can display both ferroelectricity and ferromagnetism. Bismuth ferrite, bulk bismuth ferrite shows weak ferromagnetism. The question that our hypothesis was that if we reduce the size of these bismuth ferrite particles into nano range, can we enhance its ferroelectricity and ferromagnetism? So again, we use the method called electrospinning. Here we first prepared a sol gel. This is the sol gel is the precursor of bismuth ferrite. It has got all the precursor material, bismuth ferrite precursor materials. We add a polymer. Polymer is added just so that the material can be electrospun. Once the fibers are obtained, then we heat treat the fibers. We thermally anneal the fibers. When the fibers are thermally annealed, the polymer phase gets degraded away, and eventually you get ceramic fibers, bismuth ferrite ceramic fibers. This is how the microstructure looks. The figure on the left is of fibers before they were thermally treated. You can clearly see that the fibers before they were thermally treated were uniform, smooth, etc. But after you thermally anneal these fibers, then you see grain kind of structures. We also measured the grains of these fibers. Each grain is about 20, 30 nanometers in size. The diameter of the fibers themselves were 170 nanometers. This was confirmed, the size of the grains, the size of the particles were confirmed using TEM. The average grain size we determined was 30 nanometers, roughly. Then we characterize these fibers using XRD, just to find out if the fibers that we have obtained are indeed bismuth ferrite and to determine if there's no impurity present in the fibers. All these peaks that we have obtained for this material are indexed, and they are indexed to bismuth ferrite crystals. So it's clear from our figure and our results that the fibers that we obtained are bismuth ferrite. There were a few minor impurity peaks, which can be attributed to the starting precursor materials and maybe some contamination. We then characterize its ferromagnetic behavior. In our case, these materials show clear hysteresis, and on the figure on the right is the magnetic behavior of bulk bismuth ferrite. As you can see, the bulk bismuth ferrite does not saturate, whereas our materials, they tend to saturate above when a certain magnetic field is applied. And also we see that our response is much higher. This one was about 1.5 something, whereas the bulk bismuth ferrite is only 0.2. We also used piezo response force microscopy to determine the piezo response of this material. The figure on the top is the topography image, which clearly shows again the same grains kind of structures that we saw in the TEM. The figure on the left here, bottom left, is the phase image, which clearly shows that there are presence of domains, and these domains can be switched. And then this is the response, the amplitude image. Amplitude image is when you apply a voltage, how much does the material expand or contract? Again, in this case, we saw a 180, similar to our PVDF fibers. These ones also show 180-degree phase shift when the voltage is reversed. And then the amplitude response was also similar to a butterfly loop, although we have not been able to explain why it does not show the clear butterfly loop. This one, we are not sure at the moment, but it does show the response when the voltage is applied. And when the voltage is reversed, it shows an opposite effect. Conclusion, our fibers, all our fibers that we produced, the bismuth ferrite fibers and the PVDF fibers, they both had piezoelectric properties. They both can be used as sensors and also as actuators. In case of our bismuth ferrite fibers, they were also magnetic. So which means in future, they can also be used for what is it called? Where you apply strain, it also produces voltage and it also produces magnetism, and vice versa. When you apply magnetic field to it, it produces strain and it produces some voltage. The future outlook for these is we could have these fibers, we could embed them in our, embed them in our clothing materials, we could embed them in our, as an implant to see how much it move, how much the joints move, etc. We could also use it for touchscreen sensors, on the touchscreen as part of sensors. They have got tremendous applications. People have started using this for in your clothing and shoes. They've also started putting in the clothing so you track your breathing patterns, etc. All right, that's all I have. I will also, before I conclude, I'll just thank my supervisors, my collaborators, Professor Mai, Professor Wong, Professor Liu, and Lee. That's about it. Thank you so much. And if you have any questions, again, I'll be happy to answer.
Thank you very much, Professor Baji. Everyone, let's give a big round of applause to Professor Baji. Now I would like to invite the audience to ask questions to Professor Baji. Any questions from the audience, please? Pak Purba? No question?
Yes.
Or maybe one question from me, Professor Baji. On your last slide, you showed the future outlook of the potential
Yes.
application of your research. How long would you think that could happen? I mean, what's the time scale, judging from the current rate of progress in this field?
People have already started using it. To be honest,
Okay.
people have started putting these materials in your shoes and also in textiles. Textiles is a big, is probably the next big thing. They've started, if in future you could also use the textiles to display stuff for advertising purposes, etc. That's the future. I'm not sure how soon, but for harvesting energy, people have already started doing it. You can commercially get it.
Okay. Thank you. Questions from the audience?
Have a question?
I think there's a question here on Zoom.
Oh, okay.
Yeah.
Oh, okay, Pari. Yeah, yes, please.
Okay, thank you very much. This is very interesting. Thank you very much for the presentation, and let us know about the result. And I have two questions. First about the future outlook on this one, and about the perovskite business fair. So the first one, if we want to use it for biomedical application in here, maybe we need the piezoelectric the characterization. Maybe we need to use something like smaller, because for biomedical application it looks like we didn't need the height, or maybe the such as a bond. Maybe the piezoelectric response is about picocoulomb per newton, something like that. Much smaller than the current piezoelectric material. So I wonder, do you have any facility to measure the small piezo response of the something like for the biomedical application? I think much smaller than this one.
Facility I currently don't have. This was work done when I was at University of Sydney. But we can. I can source it. I can find within our current university. We should have one in the university, piezo force response microscopy, and that should be capable of measuring even picometers.
Okay. Yeah, thank you very much. And for the second question, I wonder about the perovskite, something like bismuth ferrite, something like that. Huh? So,
yes.
Would you like to explain more about why you choose this material, and whether this is kind of permanent or permanent? Because for biomedical application, maybe we didn't use something like neodymium, the permanent magnet. Maybe it's much better if we use permanent, something like that. Is it permanent or anti-ferromagnetic? Okay.
No, this is ferromagnetic. So ferromagnetic is when you only apply magnetic field to it, and then it gives a response.
Okay. It's interesting.
And there are other similar materials, barium titanate to some extent, and we could also make other ferrite kind of materials using the same approaches. Copper ferrite could also be used using a similar approach.
Oh, okay.
It's just using the precursors and then thermally treating the materials.
Okay. So the piezo response from the PVDF or this is PVP, or from
this one is bismuth.
From the bismuth. Okay. Is it ferromagnetic?
It's ferromagnetic.
Ferromagnetic. Okay. Yeah, thank you very much. I will contact you again.
Okay.
No, sure.
Yeah, thank you, Pari, for the question. Thank you, Professor Baji, again. Everyone, let's join me in thanking Professor Baji again for the presentation. Thank you, Professor Baji.
Sure. Thank you. Yes.
Okay, now let's move on to the next presenter. The first one was a keynote speaker. Now the second keynote speaker is Professor Ari Wibowo, who is going to talk about recent advances on 3D printed electroactive scaffold. Professor Ari Wibowo is an assistant professor at the Faculty of Mechanical and Aerospace Engineering, ITB, Indonesia. He received both his Bachelor of Science and Master of Science from ITB and a PhD from the University of Tokyo, Japan. His research interests are primarily in the areas of 3D printing of smart functional biomaterials for bone and tissue engineering, nanocatalysts for wastewater treatment, and drug delivery system. Please, Prof. Ari, for your presentation. Thank you.
Yeah, thank you very much for the moderator. So in this opportunity, please allow me to introduce my research about the 3D print electroactive scaffold. I'm from material engineering, and as you know that the osteoporosis is kind of considered as the silent killer because it decreases the quality of life. As you can see in here, this is a good bone, the good bone, and this is the osteoporosis. So you can see it become more porous, and the quality of life is decreased because the mechanical properties of the bone after osteoporosis decrease. And the osteoporosis particularly occur to the elder people. And as you know, according to the WHO, about 8.9 million fracture annually. It means about the fracture occur every 3 seconds and affect about 200 million women worldwide. And normally, this is the golden standard. We can use autograft, allograph, or xenograph. However, because of the limitation of the donor, we need to focus on the other option, such as the implant. However, the metallic implant that widely used, this is only focus on bioinertness. It means they only consider about the mechanical properties. However, the mechanical properties of the metallic base implant is much stronger than bone. It means it will induce the stress shielding, and which is not good for bone growth. This is kind of different. So in the structural material, we prefer the material is bigger than the applied mechanical force. However, for bone is kind of responsive. If you apply, if they will detect if the mechanical properties of bone is lower than the mechanical of the applied mechanical strength, so they will increase the bone properties. So if the scaffold or the implant has stronger mechanical properties, it means the bone will not affect to the mechanical properties, so it will not induce the bone growth. So the second one is for the metallic base implant, we need second surgery to remove if we consider this is already good, so we need to remove it. So this is unpleasant option for the patient and expensive. Therefore, we need to prepare the biodegradable implant strongly needed. Normally, this is the requirement for the ideal bone implant. It should be 3D and interconnected porous structure for cell infiltration, suitable mechanical properties for bone scaffold, biodegradable and bioresourceable and biocompatible. These four requirements currently already provided by the current scaffold, but current scaffold mostly act as the passive scaffold. It means they only provide the temporary scaffold without considering about the accelerating the bone cell tissue. So for the elder people, this is okay for the young people, but for elder people, as you can see in here, we need at the first time after a bone fracture, the bone mechanical properties is lower than the requirement properties. But as the time they will heal, so bone itself is something like self-healing material, but for the elder people has slower healing rate than younger people. So it means if we only use the current scaffold passive scaffold, maybe the patient, the elder patient, cannot be recovered for the time being. So that's why we need the scaffold that not only act as the mechanical support, but also can act to stimulate the tissue regeneration. So in here, how to accelerate the tissue regeneration? We can use various kind of the stimuli trigger, something like Professor Baji mentioned. Maybe we can use the mechanical force to generate the electricity, and to use the piezoelectric scaffold. In here, we have various kind of the external scaffold, but at this time we focus on the electric field as the external stimulus. Why we choose electric field? Because the electroactive scaffold can deliver electrical stimulation directly to the cell and tissue. Why we use this? Because human body rely on the electrical current to carry many of function, and also the equipment for the electrical stimulation is already established, and cell could enhance the cell adhesion and proliferation and modular the cellular specification. So using the electroactive scaffold is quite established in here. And why electro stimulation can work, can stimulate the cell regeneration? As you can see in here, this is the illustration. When we apply the electrical stimulation, it will open the gate of the calcium channel in here. And as the consequences, it will enter the cell and activate the expression of the various growth factor in here. So we need this growth factor to accelerate the cell proliferation and cell growth. So by applying the electrical stimulation, we can indirectly initiate the expression of the growth factor in the bone area in here. Also, during the bone healing, cells are retreated from the surrounding, because this is the there is a uh, there's a charge in here, so the cell can attract more in here to induce the to accelerate the cell growth in here due to the galvanostatic effect. And how to prepare the electroactive scaffold? Normally, the current scaffold prepared from non-conductive biomaterial for the polymeric based material is the non-conductive. So if we want to make the electroactive scaffold, we can mix the non-conductive polymeric based material with conductive filler. We can use carbon-based filler, we can use conductive polymeric-based filler, or we can use metallic-based filler. In our case, we already prepared the electroactive scaffold using the conductive filler, using polyaniline as the conductive polymeric base, and for metallic base, we used silver nanoparticle. And this currently we publish 4 paper about this one. For the carbon base, still ongoing project. And how to manufacture the electroactive scaffold, because bone scaffold is we need to make a porous structure. But if we increase the porosity, it will decrease the mechanical properties. So we need something like manufacturing. We need a manufacturing method that can provide the precise morphology and dimension, because this is very important for the bone scaffold. We need porosity, but also we need high mechanical properties, and also high accuracy and good stability for complex system. In here, we only prepare just a simple design. We focus on the pore size in here. And we use the 3D printing machine that from our collaborator in Manchester, using this one. And as you can see, we have to prepare the electroactive scaffold, we can use the conductive filler, conductive polymeric based filler. So in here, please allow me to introduce about the this one. This is already highlighted by Professor Andy in the previous talk. Thank you very much. And as you can see in here, the average filament is about 380, and the average pore size is about 300. And the compressive modulus, we focus on the compressive term because bond is the mechanical force that affect to the bond is the compressive strength. So we focus on the compressive strength and modulus, and also conductivity in here. As you can see in here, the scaffold, the pore size of the scaffold is about 300 micrometer. This is actually the minimum for the cell that can be penetrate. So if the scaffold has the pore size above 300 micrometer, it would be beneficial for the cell to growth and penetration, and also good for the diffusion of nutrition. So it will induce the cell proliferation and cell growth in here. According to the reference, the human cancellous bond has the young modulus about 100 and until 5,000 megapascal, and the strength is about 1 until 12 megapascal. So as you can see in here, all of the all of the scaffold has the strength is about this range. So all of them from mechanical point of view, all of the scaffold is okay for the bond scaffold for human cancellous bond. And for the conductivity of the human cancellous bond, it requires about 10 minus 3 in here. And in our case is about 2.8 minus 4, so slightly lower. However, for this is cancellous bond. For the cortical bond, it's about 10 minus 4, so this is suitable for the cortical bond for the conductivity. And by increasing the polyaniline concentration in here, we can see the mechanical strength and conductivity increase, but actually it's not significant because it's already on the spec of the human cancellous bond. And according to this value, the mechanical and conductivity of the scaffold are made suitable for the specific cancellous bond. So we need information about the bioelectrical response in here, because from the mechanical properties, from the conductivity point of view, this is actually already on the spec. So we apply the mechanical, the bioelectrical response in here. First, we are studying about the cell viability. This is the first day. This is the after day 21. The green one, it means cell was live in here, and the right one, it means cell already dead. And as you can see, the PCL as the baseline in here, you can see at the day one, more than 50% still live. It means the cell, it means the PCL is not toxic if the cell viability is more than 50%. And it's also applied for the polyaniline 0.1 and 1%. We can see a lot of green area in here, and the cell viability for the day one for 0.1 and 1 is more than 50%. And interestingly, for the by the addition of the polyaniline 0.1%, the cell viability increase. And after that, after 0.1, 1% and 2% already toxic, because for 2% lower than 50%. After day 21, we can see that still in polyaniline 0.1, green area still a lot in here. It means cell viability for the polyaniline 0.1 is still okay, and more than the cell viability of the PCL. However, for the polyaniline 1% and 2% already toxic, because you can see no green area in here. It means cell already there in here. So from the self-viability point of view, we can see that 0.1, polyaniline 0.1, is the most suitable for biological application, because for 1% and 2%, even though the mechanical properties and conductivity increase, but after day 21, it's already toxic. The second one about the biological response is about self-viability. So cell proliferation, as you can see in here, the 0.1% has higher cell proliferation than the PCL, and also for the PCL 1% and 2% is lower than 0.1. This is because the cell in here maybe by increasing the concentration of the polyaniline, there's byproduct from the polymerization release and become a toxic for this material. So 0.1, if we add 0.1, it will increase the proliferation of human adipose derived stem cell about 20% compared to the PCL. And please allow me to share about our result about metallic-based nanoparticle, electroactive scaffold. So we are published in Molecule in here, and very recently, November 2023, we published in Material Advance. So here the pore size in this case, we use different design. The previous one we just prepared 300 micrometer. However, we think that we have a problem with the blocking in the nozzle. So we increase the pore size, but we also increase the filament size. And according to this value, human cancellous bond, if we use the PCL, only PCL, and with this design, the the compressive strength of the PCL is lower than the minimum requirement for the human cancellous bond. However, by additional of 0.1 silver nanoparticle, it will increase significantly, 6-time increment from 0.65 to 3.88. And this value is meet the requirement for the human cancellous bond. And also by the addition of the silver nanoparticle, we can increase the conductivity, become suitable for the bond scaffold. And also we can see in here, since the silver nanoparticle have antibacterial effects, so we can see that without the silver nanoparticle, only the PCL, we can see in here by the addition of the silver nanoparticle, we can decrease the we can decrease the bacteria live in this scaffold about 99.5%. And also by the addition of the silver nanoparticle, we can reduce the contact angle in here. It means it will increase the adhesion of the cell to the PCL and the silver nanoparticle scaffold. So we are studying about how the cell attachment, cell proliferation after this. And as you can see in here, for the PCL, this is the PCL and this is the PCL silver nanoparticle. There's a stretching line in here. It means the cell growth better in here. And this is the confocal microscope result taken from the bottom of the scaffold. It means the blue one is the staining agent for the nucleus of the cell. So as you can see in here, for the silver nanoparticle, with the addition of the silver nanoparticle, the cell can penetrate to the scaffold, and the silver nanoparticle can induce the higher cell proliferation. And we want to know about, is it the silver nanoparticle can really induce the cell proliferation and osteogenesis. So we are studying about gain expression result in here, and also as you can see, the gain expression, the most important gain is RunX2 for the cell growth. And as you can see in here, the RunX2 gain in the silver nanoparticle has the upregulated 2 until 3 times than the PCL scaffold itself. So very positive result for the cell expression. And also for the protein expression, we use two protein here. The first, the collagen type of the collagen type 1 protein. Red one, it means the collagen 1 protein is expressed in here. So if we use only the PCL, we didn't see any. If we use the control, we rarely see the expression of this collagen type protein, but on the PCL we can see in here. But for the silver nanoparticle, the expression is better in here. The information in here is important for us to know about the which stage in after day 7, 14, and 20. According to the literature, collagen type 1 protein is expressed during the pra-osteoblast, immature osteoblast, and mature osteoblast. So it means we could say that day 1, day 7, day 6, this is correlated with this one. So we need more evidence to define the expression scheme. So in here we use the osteopontin protein. The osteopontin protein is the expression is identified by the red particle in here, only observed after day 21. And according to the literature, osteopontin has the highest expression and the mature osteoblast. So it means in here it's already started the mature osteoblast stage of the cell in here. Until up to day 14, still not mature yet. So according to this information and also from the gene information, we can propose the schematic representation of the cell osteogenesis drawn in the PCL scaffold. This is the transcription factor, and the red one in here based on the gain expression, and the blue one based on the protein expression. Since the osteopontin only started expressed at day 21, so we can say that the osteopontin in here, we can say after day 21 it's already mature osteoblast, and in here still not expressed yet, and we can also observe the collagen 1 protein. So this is the mature osteoblast occur starting from day 14, and pra-osteoblast starting from day 7. So according to this result, we can see that the addition of the silver nanoparticle on the 3D print PCL scaffold can increase the cell proliferation and also can induce the osteogenesis in the human wharton jelly mesenchymal stem cell. And I would like to acknowledge this funding from our government, from Ministry of Research and Technology and Higher Education, and also the funding from the ITB, and also funding from special funding to our faculty. And also I would like to thank to our collaborator from Professor Paulo, NTU, and then Manchester, and Glenn Cooper from Manchester, Hein Freas, previously graduated from Manchester and right now postdoc at NTU, and also Professor Andy, Professor Tata Cipta, Professor Husaini, and Professor Anggaini Balian from the ITB, and Dr. Lia, and also for former students. Thank you very much for your attention.
Thank you very much, Professor Ari Wibowo, for sharing with us impressive work and also encouraging results with your research. I would like to invite questions from the audience, please. Yes.
Thank you, Dr. Ari Wibowo. It's interesting research, I think. I would like to know the technique of 3D printing you use to print the scaffold. That's all. It's very interesting. Thank you.
Yeah, thank you very much for the question. So we use Fuse FDM. So in here, the matrix was mixed with the conductive filler. We mix it using, we didn't want to use the solvent in here, so we just heat it to let the PCL melt it, and then mix with the conductive filler, mix it, so we call it the blending method. After that, we get the premix that consists of the conductive with the matrix, and then after that, we put the premix inside the hopper in here. So the hopper, and then we apply the temperature about 90 degrees Celsius, which is much higher than the melting point of the PCL, about 60 degrees Celsius. And then by applying this temperature, the mixing the premix will to printing like this.
Answer your question, Pak.
Okay, you use FDM. Okay, that means you make your own filament for that.
We didn't prepare the filament, so we prepare the premix, put it the hopper in here, the premix of the PCL and the conductive. We mix the mixing in here after the nozzle, it becomes something like this. So just like the kind of the film, but it's not a film. The diameter of the filament is related to the diameter of the nozzle. We use 500, about 500 microns per nozzle.
Okay, thank you. I need to read more about your publication previously, I think. Thank you.
Thank you very much.
Thank you, Pak. Other questions, Pak Purba?
Okay, next presentation, Prof. Ari. I have a question about you use the polyaniline
Yes.
for the mixing for the conducting polymer. So I'm curious about because of you mentioned about the development for the bone scaffold. For the long time, I worry about the compatibility. Even if we use only about 0.1%, is it any information about the cytotoxicity above like the 30 days? And the second is, I'm curious about how about the bone mineralization process? Is this, you did the study or not about this one? Thank you very much.
Okay, thank you very much for the question. Yes, polyaniline, there's two groups have a report about the polyaniline. So the first group said that the polyaniline is toxic and not suitable for biomedical application, and the second group said that actually polyaniline is okay and non-toxic, and also can induce the cell proliferation. And these two groups, actually, I think both of group is true. Both of them is correct, but the difference only the concentration, because if we apply just like water is not toxic, but if you drink too much water, it will become toxic. And in here, we need to find the correct concentration, which is not toxic and induce the cell proliferation. To to the best of our knowledge, normally the cell viability only doing until 3 days and sometimes only until 7 days. So in this case, our study until up to 20 days, 21 days is the longest cell viability study for this one. So because previously we only observe the cell viability only apply until 3 or 7 days. So at least in here we can see the growth in here, and we can see the cell viability still okay until day 21. We didn't know actually until let's say 1 year we didn't have any data at this time. And this is our further study. We are trying to collaborate with someone from the bone surgery, something like that. We want to know the longer effect. But at least until day 21, we didn't see any toxicity. And based on this result, still the cell viability of the the polyaniline 0.1 is higher than the PCR itself. So this is kind of promising. Of course, we need to do the study. Let's say for the polyethylene glycol itself, it's say from the FDA, polyethylene glycol is FDA approved, but someone testing after several years, it occur the polyethylene glycol sometimes have the rejection from the body. So long term, we didn't have any data yet, but this is quite good for collaboration for further research using the bone surgery, something like that.
Does that answer your question, Pak Purba? Yes. What about the bone mineralization? The second question for
Yeah.
Pak Purba. Yeah. Okay.
Yes, thank you. I forgot. I'm sorry. Bone mineralization, we didn't until day 21. We didn't check the bone mineralization. However, as you can see in sorry. In terms of the cell attachment and also cell attachment and also cell change to the osteoblast. This is important for the cell for the bone growth. In terms of this one, we can see that by applying the silver nanoparticle in here, it's already become a mature osteoblast after day 21. It means the cell, mesenchymal stem cell is kind of the flexible. They can change anything, and depend on the situation, depend on the environment, they can modify differentiation. And in this case, because we want to apply for the bone, so we expect the mesenchymal stem cell become a osteoblast. So according to this result, we can say that after day 21, the mesenchymal stem cell become mature osteoblast, which is very important for cell growth in here.
Okay, thank you very much, Professor Ari. I think in view of time, we should end the presentation from Professor Ari Wibowo. Everyone, let's thank Professor Ari again for his presentation. Thank you, Professor Ari, for joining us. Thank you.
Yeah.
Now let's move on to the next presentation. Next speaker is Mahros Darsin from Jember University. Pak Mahros, floor is yours. Okay.
Where to stand? Here or? Hah? Slide-nya. Already sent. Sudah dikirim. Ada? Slide-nya sudah? Sudah dikirim, ada? Oke. Okay. Thank you, everybody. Good afternoon. I would like to present our result. Result. This is heat treatment and its effect on tensile strength of FDM 3D printed titanium PLA. Yes, myself, my student, and our colleagues there. Yes. Okay, next. This is the presentation organization, my background, and research method, result and discussion, conclusion, and future works. Next. Okay. Next, I think. Too much, that one. Next, please. Okay, the previous studies about Giant et al., 2021. The tensile strength of 3D printed PLA increased by 80%. After heating at 1000 centigrades for 4 hours. And Kacha 2019, the tensile strength of 3D printed PLA increased by 26.9 MPa after heating at 80 centigrades, and its bending strength increased by 26.6 MPa after heating at 60 centigrades. Ambrose et al. 2021, post-processing of PLA removal on 3D printed copper PLA increased the hardness of the specimen up to 9 HV. Next. So our study is about how to remove the content of PLA from PLA titanium printed. Yeah. Okay. So what is the effect of the temperature and holding time during heat treatment to reduce PLA content? Yeah. On the tensile strength and microstructure of 3D printed titanium product using titanium PLA filament. And then what are the characteristics of those? The optimal temperature and holding time values during heat treatment to reduce PLA content and the maximum tensile strength value of 3D printed titanium product. Yeah. Okay, next. Okay, the objective, knowing the effect of temperature and holding time to the tensile strength, and also we observe the microstructure, and then we find out the optimum temperature and holding time to get what is the maximum we can achieve by reducing the PLA content, but the tensile strength still okay, it's still acceptable. The benefit will provide new information regarding the influence of heat treatment, and then as a reference for the future studies of the using PLA titanium filament. Next. Okay. Okay. So we didn't look for. We just concentrate on the heat treatment and the effect to the tensile strength, and we didn't look for the best parameter of 3D printing titanium because already done by other researchers, and we do not discuss the parameter beside the temperature and heat treatment because we did only these two things. Doesn't discuss 3D printing electricity and the test carried out with thermography metric analysis, TGA, tensile test, and micrographic evaluation. And our hypothesis is specimen will experience a decrease in mass according to result of TGA after being heated at several temperature phases. And then the decrease in mass due to temperature is not necessarily directly proportional to the increase in tensile strength value. Next. And we use the normal, the conventional 3D printing under 3D 3D printing machine, and we use muffle furnace, the old one. You can see the rust. Okay, and we use a universal testing machine for testing the tensile styles. Okay, next. And we use optic microscopy, TGA, and digital weight. Next. Okay, the material is titanium filament. Yeah, titanium PLA filament. We bought it, imported from America, and this one is quite expensive, especially if you come to the import rate and the Papian, with just the tax is very high. Okay, yeah. Okay, and we use resin and catalyst for analysis. Next. Okay, we use our research variable. We use temperature 4 times, 100, 160, 190, and 543 degrees. And then holding time 60 minutes and 120 minutes. And this is the one controlled variable. Bed temperature 50 centigrades, nozzle temperature to 125. All of these control variables according to the manufacturer suggestion. And we will see the microstructure, tensile strength values, and specimen mass. Yeah, reduction of the mass of the specimen. And this one, we found it from TGA analysis, the maximum we can find. And the others is just for the variation. Next. So we will discuss about the result and discussion about 3D printing result, TGA, heat treatment, mass reduction, tensile strength, and microstructure. Next. Okay. So we make 3 types of specimen, tensile test specimen. We print, our specimen is like this, and this is for TGA specimen, which is accommodate the machine or the TGA machine for the testing. And this one is for micrography specimen. All are with the variation we already mentioned. Yeah, the variation of the variable. Next. Okay, this is the thermographimetric analysis. According to the temperature here, 100, 200 until 800. You can see the DTG, milligram per millimeter. The mass reduction is something like this. Yeah. If we increase the temperature, the mass will be reduced, and then the maximum is about here. Yeah, 400 plus about, yeah. And this one, at a temperature 543 degrees, mass reduction is 22.18%. This is about the same as the specification of the filament itself. The filament, according to the manufacturer, is 80% titanium and 20% of PLA. And another composition they didn't mention. Yeah. So after this temperature, we imagine that, we assume, that is not imagine, we assume that in this temperature, all of the PLA has gone. Yeah. The rest is the titanium. Next. Okay, we did the heat treatment of the specimen at 100 centigrades and 60 minutes. The condition is, we can see, and compared to 120. And then start from 190 and 60, you can see the mass or the volume look like reduction. So it will a curve there. And this one with the longer heat treatment, 120, already curve is will be more clearer. Yes, more clearer. Yeah. And at 540 degrees, the specimen is already gone. It's like the dust. Yeah, because actually the 3D printed, this one is for 3D printing using FDM. The main filament is from PLA, But the titanium itself is what do you call, apa namanya? Pengikatnya itu PLA-nya. Because after heat treatment of this, already gone 22%. That means all of the PLA already gone. We assume like this, yeah. And then the specimen like dust, yeah. We don't need to test it for the tensile strength. Next. Already happened, look like the same, but we didn't do the heat treatment until 542 degrees because our experience and that temperature already gone. If we do it, we cannot see the microstructure of the specimen. Next. And this is the mesh change, yeah. At 543 degrees and 60 minutes to 22.44 and 100 same one, but it look like the same, yeah. The mass reduction is about 22%, yeah. Maybe this one, as I mentioned earlier, the composition or the content of PLA already gone. Okay, next. Okay, this one is meshing micrograph. Because we didn't do the 543, the reduction is the maximum only 4.5%. Next. And then this is the tensile strength result. We can see all of the result we observe macro observation. The fracture is good. That means not on the neck or neck, yeah, but in the middle, it's okay. Okay, next. And this one is tensile strength. Stress and strain of different heat treatment. Yeah, you can see here for non-heat treated. Yeah, you can see the tensile strength is quite okay, but such heat treatment will reduce the tensile strength. But this one we cannot accept this one. 190 and 120 minutes. We cannot accept this one. So I think this one is the best. 160 and for 60 minutes. Yeah. This is still acceptable. That means we try to reduce the PLA, but the tensile strength still okay. It's still acceptable. Next. This one, all of the observation we've done, this is the one we choose and we recommend. Yeah. Next. And we see the microstructure, the titanium and the PLA before we do 3D printed. That means this one is the specimen after 3D printing. Yeah. Without heat treatment. It's quite good. Everything is merata itu apa ya? Homogeneous. Sorry, my English is broken. Okay, next. Okay, this one after specimen after 190 degrees of heat treatment and for 120 minutes holding time. Some pile up here of PLA, yeah, particle titanium pile up here because some of the PLA are already gone, and so pile up of what do you call in material science? You can see it. Okay, next. Okay, this is the conclusion. Heat treatment carried out with temperature and holding time parameters does not make the tensile strength value of the specimen increase compared to non-heat treated specimen. The best parameter to produce optimum tensile strength of 3D printed titanium specimen are temperature 160 degrees and holding time 60 minutes. And there's no known composition content that decrease or increase after the heat treatment process. Okay. Future work, next. Okay, heat treatment should be used at use vacuum furnace to avoid porosity. And also, the titanium is, what do you call, easy to connect, easy to make connection with other material. So we use, we have to try use vacuum furnace. Then, okay, and we also try to looking for temperature and holding time. Yeah, that can increase mechanical strength. And next, should do SAM, EDS, XRD. Okay, that's all. Thank you.
Thank you very much, Pak Mahrus, for your presentation. I would like to invite maybe only one question from the audience. Pak.
Thank you. When we saw the microstructure, I think there is no sintering effect for the titanium powder.
Yes.
Can we make sintering effect for the titanium powder by 3D printing? That's the first question. And the second is, when you make the sample, tensile strength sample,
yeah,
it's directly formed to the sample, or you make by
cut. A block
only
and cut.
a bar, and after that make machining.
No, yeah. For the
That's
second one, we print directly. Yeah, according to the design. Yeah, and then the second, the first one, actually our idea come from what do you call? Sintering. Actually, our idea is how to make sintering of this process to remove PLA. Yeah, because we want, like Prof. Ari previously, use this titanium as a bone or as a scaffolding or as an implant, bio implant. Titanium is good, but make titanium, process titanium to make bone implant, usually use another technique of 3D printing, SLM, SLS, but we try in 3D printing, we're using this FDM, usually only use plastic, made from plastic. But this available, titanium PLA. But the PLA is the problem if we use as a bone implant. Actually, PLA itself is biocompatible, like titanium, but it is biophobic. That means probably will attract the disease or some bacteria to go inside. That is the problem. That is what we want, the idea to reduce or to get rid of the PLA after printing. Yeah, that is. Yeah, the idea is from sintering process, but not succeed yet. Thank you.
Okay, thank you, everyone. Let's thank Pak Mahrus again for his presentation.
Yeah.
Okay. Thank you, Pak Mahrus.
Thank
now
you.
let's move on to the next presentation by Dr. Purba Purnama from UPM Indonesia. Pak Purba will present his work on bio-based materials stereocomplex polylactide as a nucleating agent.
Okay, good afternoon, everybody. Thanks for your coming to my presentation. Today, I would like to present about my work about bio-based material stereocomplex polylactate as nucleating agent. So this is the overview of the outline of our presentation. I will introduce about the PLA and stereocomplex, how to formation the stereocomplex, and then I would like to share about the stereocomplex application as nucleating agent. Okay, so this is the basic about the polylactate. Now polylactate is used for many applications like the automotive and mostly in biomedical application. But PLA itself has some limitation in terms of mechanical and thermal properties. So now we form the stereocomplex polylactate and use it as a nucleating agent. So it will improve the thermal and mechanical properties of polylactate here. So as we know that the material development now is the shift from the fossil polymer to the biodegradable polymer. As we can see here, now the expected production capacity is biodegradable will be higher, and most of them will be based on the PLA, including like the PLCL and others material. Recently, regarding the material development, the future material development focus on three factors. One is about the sustainability, because we need focus about the renewable resources. The second one about the degradability. It's related to the environmental concern. And then the third one, in terms of the polymer material, about the property sustainability. Because for some specific application, we need to some specific mechanical and thermal properties. So I want to introduce about the PLA. This is the polylactate. Maybe Pak Maros already mentioned before about the PLA. This is the biodegradable. And then it's synthesized from the bioresources material like the corn. It becomes the starch, lactic acid, and then make the oligomers and form the lactate. To form the high molecular weight lactate, we cannot directly from the lactic acid, but we need to convert from the lactate using the ring opening polymerization to obtain the high molecular weight PLA materials. And then for the PLA material application itself, we can see here, there are a lot of application, like the packaging material, single-use material like the spoon and others. And then it's also used in the electronics above. And then mostly PLA used in the biomedical application. So related to the 3D printing, there are a lot of potential application in biomedical application using the 3D printing as mentioned by Prof. Ari before. But I want to inform about there are some limitation of the PLA. Okay, in terms of they have a lot of advantages related to the bioresource material and eco-friendly material. It also has disadvantages. For example, like the strength and durability, and also the heat resistance. This is related to the mechanical and also the thermal properties of the PLA. So we need to modify the PLA into the high strength and high heat resistant application. So let's back to the basic of the lactate itself. It consists of three types of the isomers. We have the L-lactite material, and then the second the D-lactate, and then the third one has the meso-lactite. So when we polymerize these lactate monomers, so we can have three types of the polymers. One is the PLLA, PDLA, and also the PDLLA. With the different tacticity of the PLLA and also PDLA, we can utilize this different tacticity to form the stereocomplex polylactate, which has different crystal structure compared to the PLLA itself. So how to what about the stereocomplex polylactate? Here, from the PLLA and PDLA here, which has the different tacticity here, and then we mix and then we co-crystalline, it will form the hydrogen bonding between the PLLA and also the PDLA, and then it will have the new crystal structure. With this new crystal structure, it has the different properties compared to the PLLA itself, such as it has the higher thermal property, melting properties. For example, the melting properties for PLLA is about the 160 degree until to 180, but using the SPLA crystal structure, the melting temperature, it will increase above 200. Normally, I got around 230 degrees C for the melting temperature. The another thing is it has the higher mechanical properties and also the higher impact strength. So with this kind of the properties benefit, we can use this as a potential for the additive materials. Before the application of the additive material, I want to share you about how to synthesize the stereocomplex polylactate. So as mentioned before, we mix the PLLA and PDLA to form the stereocomplex polylactate. For the mixing, we can use the several type of process. We can use the solution casting, melt blending, microwave irradiation, and also the supercritical carbon dioxide. So I show you here, we make the stereocomplex polylactate using the supercritical fluid. The supercritical fluid is the phase of the material above its critical temperature. So you can see here, the material, the solvent, when in the normal condition, it has the liquid and also vapor phase. But when we increase the temperature and pressure, it will become homogeneous. If achieve the higher the critical temperature, it will form the supercritical fluid condition, which is the supercritical fluid condition. It has the specific benefits. The density is similar to the liquid, but the diffusivity is similar to the gas. So it's mixed the properties of gas and also the liquid. So using this supercritical fluid technology, I'm from the stereocomplex polylactate. This is the schematic diagram. We use the high molecular weight polylactate. We use the carbon dioxide gas. We add the co-solvent, the chloromethane, and this is the scheme. And then using this system, I can obtain dry and also the powder shape of the stereocomplex polylactate, which is difficult to obtain in the powder shape when we use the melting process or solution casting process. And then here we can show that we obtain successfully 100% of the stereocomplex polylactate because when we see the melting temperature, it's shifting from the 180 to 230 degrees C. And then based on the crystalline structure, we can also see it has a different XRD thermogram here. So using the system, we can successfully synthesize 100% of stereocomplex. And then we apply this stereocomplex as a nucleating agent here. So at the first works, we compare the stereocomplex polylactate and the PDLA as a nucleating agent. From this, we can see here, for the mechanical properties, it improves the tensile and the Young's modulus when we use the stereocomplex polylactate compared to the PDLA itself. Then another thing here, we use the second heating using the DSC, different scanning calorimetry. From this, we can see here, the second heating, it's already higher, so it can still maintain the properties of the stereocomplex polylactate. The another thing that we evaluate is about the co-crystallization temperature. It's already shifting from the base polylactate is increased here with the addition of the stereocomplex polylactate with the blue color. Okay. And then it's also the heat of melting of the material consists of the stereocomplex polylactate is also increased here from 1 until the 5%. And then we also study about the crystallization process for the nucleation here. For the neat polylactide compared to the addition of the PDLA and also the stereocomplex polylactate, we can see the nucleating initiator, it's higher when we add the stereocomplex polylactate compared to the original or also the PDLA. And then the another one, we also add the stereocomplex polylactate particle to make the formation of SPLA itself. So here we use this different particle size from the smaller until to the bigger one. And then the smaller particle size, it has the bigger effect on the crystallization of the material and also the degree of the stereocomplex polylactate. It's also confirmed with the XRD thermogram here with the presence of the peak of the stereocomplex polylactate here. Okay, and also the mechanical properties is also increased. Here, when we use the addition of the SPLA, 10% here, we can see the tensile strength is higher compared to the original PLLA and PDLA formation. So this is the conclusion of my talks. We can use the stereocomplex polylactate as the additive of the polymeric material. And then the second, the presence of the SPLA need to limit it at certain level, because if we have the SPLA at higher content, it will affect to the brittleness of the material. Okay. The SPLA has more effective nucleating effect compared to the PDLA homopolymers. Okay. And then the material modification can support the material tunability for the future application. And then in the future, we still on ongoing process for the continuous process of the stereocomplex particle formation, because this is promising for the industrialization. Thank you very much for the attending my presentation. Thank you.
Sorry, I couldn't catch what do you mean by nucleating agent, and then the future work is for industrialization. What for? The next, I mean for next future, what for after you find SPLA?
Okay.
That's it, thank you.
So for the nucleating agent is we add some material to improve the crystallization of the polymer material. Okay, so here we use the PDLA and also the stereocomplex polylactate particle. For the PDLA, it will form some part of the stereocomplex itself. But we directly add the SPLA, and that is increased higher compared to the PDLA itself. If we use the PDLA only, it will costly, because the price of the PDLA is more than 5 times the PLLA itself. So if we use the stereocomplex polylactate, it will more economically. So only the half content of the PDLA material that we use in the stereocomplex polylactate. And then for the continuous process of the stereocomplex polylactate particle, we can use the SPLA for the biomedical application and also the another application. With this combination of like the PDLA and also PDLA, we can modify the structure of its polymer. Like previously we modified the PDLA with some caprolactone. It will become more flexible, and also the heat resistibility is more better. So if we can produce this continuous process using the stereocomplex polylactate, we can obtain the stereocomplex polylactate in the powder shape, and also we can control the particle size. The smaller particle size into the nano size, it will be better and has the better effect to the material. Thank you. Yes, now we plan to work with Pak Zaki to use this stereocomplex particle to be applied in the PLLA, and then we want to use the 3D printer. Thank you.
Thank you, Pak Purba. Any more questions from the audience? Okay, if not, let's thank Pak Purba again for his presentation. Thank you very much, Pak Purba.
Okay, thank you very much.
Now let's move on to the last presentation in this session from Pak Tono Soekarnoto from Universitas Trisakti, who's going to talk about the properties changing of aluminum ring washer for oil drain plug after repeated use.
Good afternoon, everyone. I will present our paper. This is the research conducted by our student Lita Safitri, and I am the supervisor. Next, please. As we know, aluminum ring washer was used for oil drain plug in crankcase or other. The combination of the plug bolt and with aluminum ring washer is effective to preventing seepage, oil seepage around the drain hole. In practice, it's often found that the aluminum ring washer are not used for oil drain plug, or some mechanic change with seal tip to prevent oil seepage. Next, please. Usually, ring washer made from soft material, soft metal like aluminum, copper, or brass. After bolt tightening, the plastic deformation will fulfill the gap between the bolt head and the case. So it prevents from seepage. By this mechanism, no need high torque bolt tightening. And also the ring washer must fulfill to heat and chemical resistance for, in this case, is engine temperature and oil. Next, please. This is the reason why we make experiment or research about this ring washer, because we found many times the misuse of seal tip for oil drain plug. At the first time, seems that using seal tip successfully to prevent of seepage, but after that there is negative effect like the thread worn and the oil can still leakage or the seepage occur. Like the left picture, this is the oil pan of motorcycle, and the right photograph, I mean the left and then the right photograph, the oil drain plug is coated by seal tape. Next, please. Maybe you can play the video. This is we get from YouTube. Many YouTuber posting tips or recipe to prevent leakage in oil drain plug. The video show they use seal tape and claim that this method is effective to prevent leakage. Okay. Nah, after sometimes there will be thread worn. Nah, because it occur in the hole, it's difficult to repair. This one is use glue or to repair the thread worn. Maybe you can stop this and switch to the other video. The first one, can you stop the first one? Okay. That using seal tape. It seems easy and effective, but this method is not a proper method. Now, this one is the correct procedure. We use, they use new ring washer. Replace the old one with the new ring washer. Okay, I think it's enough. Thank you. Next. The objective is to examine the changing of aluminum ring washer mechanical properties after use, and to answer the question about is it appropriate ring washer will be used repeatedly. Next, please. This method, we make simulation by using torque for ring washer, and after that we examine the hardness and treat annealing, and also make microstructure examination. Next, please. This is the material and equipment. The left one is the bolt and the ring washer. In that photograph, we use two-layer ring washer. Diameter is 14 millimeter, inner and outer 22 millimeter. The thickness is 1.5 millimeter. We use torque wrench to adjust the torque. We use 50 pound-feet or 68 Newton-meter torsion. Next, please. Annealing, we use cooking oil with stove, electric stove, and measure the temperature for 200 centigrade for about 5 minutes. Next, please. This is the equipment. For measuring the thickness, we cut the ring washer and make some kind like microstructure sample and measure by hardness machine. So we can measure with Vickers method the diameter, but in this case we measure the thickness. This is the ring washer after we test hardness with Rockwell A. Next, please. New ring washer before we were using has hardness of 29.7. Then after deformation by load 50 pound-feet, increase to 48.1, and the third bar is hardness from ring washer after loading 2 times by torque 50 pound-feet and annealing. And the right one is with no annealing, the hardness increased to 71.3. Next. I have mentioned the changing of hardness. The strain occur by twice loading is 24.5%. And from this result, we know that without annealing, the hardness increase almost more 200% than as it is. So in this condition, the ring washer is not proper to use again. Next, please. For the conclusion, the aluminum ring washer increased from 29.7 to 48.1, and by annealing we can reduce hardness to 32.8. Aluminum ring washer can be repeated use but not recommended for more than twice due to increasing hardness and the ring become too thin. This is our sadness about the multiplication of wrong procedure using seal tip for oil drain plug through the social media, or in this case we found from YouTube. I think many mechanics make idea to use this using seal tape rather than change the new ring washer after changing the oil. Thank you for the attention.
Thank you very much, Pak Tono, for your presentation. I would like to invite questions from the audience, please. Pak Andi.
Thank you, Pak Tono. I'm Andi. Very interesting investigation. Of course, I don't know whether if you go to authorized service place, would they always replace the ring washer? Would there be in the maintenance manual, for example, that they have to follow what components has to be replaced, change, oil change and everything. But of course, then we have all this that are unofficial places, bankels, that might do this. So I think I would like to know whether there is this. Maybe we could, if we do need to socialize, maybe also a good point to have to invite also the companies, the automotive companies, the publican or this to do this, because this is it's not a good engineering practice. Thank you.
Thank you, Pak Andi, for the suggestion, and I answer your question. According to manual book, in the official workshop, they change, after changing oil, they use new one, the new ring washer. And this small part or simple part is occur in the bill. I have ever seen that the price is 10,000 rupiahs for this small ring washer. But I don't know why the aluminum ring washer is not can be buy in every small spare part shop. I think this is because this condition make some unofficial workshop cannot find the new ring washer. But after marketplace or online market occur, we can easily buy aluminum ring washer. That's my answer.
So maybe the idea is to educate the masses that just buy a new one, But of course, maybe interesting to check also the quality of the online available, available online the ring washer.
Oh yeah.
Yeah. Okay. Thank you.
Thank you. The problem is the thickness of the ring washer is not standard.
Thank you. Interesting research and from practical daily life. I think you do the test. What do you call test?
Torque wrench. By torque wrench.
You imitate the work of the mechanical when you tighten the ring washer.
Oh, the torque load we choose 50 pound-feet is compared with the tightening torque of oil drain plug.
Okay. Why don't you just simply test the ring after use? I mean, when you change your oil and then take the aluminum ring washer and then test it.
Yes, we have done the real use ring washer, but this is the sample from simulation we have used.
I mean, I think it will be better if you compare it to the real one.
Okay, thank you.
The real one. This is the experiment, and this one the real ring. I think it will be better to see the result.
Because if we use the real former ring washer, we have no information the torque loaded before.
Yeah, of course.
Yeah.
But I think the mechanics, they don't use the measure for that. Just perkiraan. Yeah, just like that.
Yeah.
Okay, thank you.
Thank you, Pak Maros.
Yeah.
Okay, I think it's time to close this session. Let's thank Pak Tono again for the presentation, and also all 5 speakers in this session. Thank you very much for your presentation. Now I think we should wait for the other session to end, and I think maybe this panel will be open for the last session. This, second.
What about if we take Untuk together?
Maybe that's a good idea. Yeah. The speakers.
Recording stopped.
Tadi Pak Ari Wibowo udah Pak Ari Wibowo masih online karena nanti ada lagi ya. Jadi wah ini kayaknya session terakhir kita di sini bakal mepet-mepet nih orang ini. Katanya nggak bisa, nggak keburu katanya. Soalnya ini kan biasanya lunch time. Ini cuma kopi. Ya. Ya udah nggak apa-apa lah, tapi bagusnya jadi kelihatannya kan ini kan kelihatannya sesak gitu loh. Closing ceremony sesak. Kayaknya mesti di sini Pak. Ya, sebab kita masih ada technical session terakhir. Salah satunya pakai Zoom. Ini kalau Zoom kita Pak, thank you Pak.
10 minutes ya?
Oh,
10 minutes ya? Enggak, maksudnya saya akan coba 10 minutes speed up.
Ini, iya, masih banyak yang itu. Kayaknya kita harus panggil-panggil nih. Iya, panggil. Ya, hanya Pak Arif yang bisa. Kalau sama kita nggak nurut nih. Kopinya bawa sini. Kopinya bawa sini, betul. Harus cek yang manggil dulu, Pak. Siap. Belum tanya dulu. topic is about AM in education. Mostly because we are the chairs, we are all educators, we are all lecturers, and we want to be able to infuse more and more of or implement AM in our classes in teaching next generation engineers for design and manufacturing. So we decided to have this session. Pretty much it's only Professor Ari Wibowo from Institute Technology Bandung that is the external. Others are basically all in the chairs. Oh, oh yeah. All right. So let's start. The keynote seminar for this session will be given by Dr. Zaki Zaldi. I think no need for introduction. This is like 2 keynote and like 2 invited speaker and many session chairs. Dr. Zaki Zaldi is the study program head of engineering product design in University of. Previously. Okay. Oh, okay. Yeah. He will present actually 2 cases where he infused additive manufacturing in education. So without further ado, Dr. Zaki Zaldi, the title is Additive Manufacturing in Education, 2 case studies. Please, the floor is yours.
Thank you, Pak Arif. Hello, everyone. Okay, so additive manufacturing in education, 2 case studies. In this session, the motivation is, of course, driven by our shared interest in the additive manufacturing. There's also one particular reason why I think additive manufacturing is going to be the way forward, especially in Indonesia also, is that we have now easier access to more affordable 3D printing, especially the one which is extruder-based FFF or FDM. On top of that, beside the hardware itself, beside the printers itself, we also have easier access to 3D software. There are now lots of, let's say, free license software for educational institutions. To name a few, we used a lot of simulation using Autodesk Fusion 360, which has lots of features that we can actually make the best use of. So what I'm going to show you today is how AM impact teaching and learning in higher education. So that's the first perspective or the first study case. And the second one, in Indonesia, lecturers are also required to do community service. And through community service, actually we can also educate a wider community. In this sense, in this case, we obtained a grant, community service grant from the government, where we use that grant to actually educate vocational high school teachers to use AM or 3D printing in their teaching and learning. So the second case studies is in vocational high school setting. So those are 2 case studies that I would like to show you today. And this work is actually all about the works that I had when I was still with my previous university, Universitas Prasetya Mulia. Recently, I joined other university, but all of the results that I'm going to show you today are when I was still with Prasetya Mulia University. So, teaching and learning here, what I'm going to show you is related to how AM was implemented in product design engineering study program. So I joined Prasetya Mulia back in 2016, and we developed this curriculum. And with product design engineering, we know for sure that I think 5 years ago, AM 3D printing was still, well, not so many universities use 3D printers, but we learned that this could be the way forward because it looks really interesting. It looks really interesting for students actually to realize their ideas to build prototypes, product prototypes. So what I'm going to show you is some illustrations of products developed by our students using 3D printers in 3 representative examples courses. First one is Design Project 1, and then there is also a course called Computer Aided Engineering, and the second one, of course, in final projects. I think all of you have the same experience. In final project, we also use 3D printers to develop prototypes. And the second one, I'm going to show the community service program that we conducted at SMK, or Vocational High School in Cianjur. So for the first one, the case study in teaching and learning in product design engineering. So the TNL, the teaching and learning in PDE program at Prasetya Mulia University, is actually design driven. What I mean by design driven is that students are trained to think creatively and also using critical thinking. So not only that they are required to master design skills and technical skills, but of course, they have to be able to identify problems and also to define problems correctly. And based on that, they should also be able to exercise empathy towards consumers or towards users. I think Professor Wang yesterday showed a very nice example of how biocompatible products or implants can really help people. And in order to be able to define that problem correctly and identify the problem correctly, empathy is really important. So that is what we also want, that value is what we also want to train our students. Of course, creativity and also problem solving, collaboration, critical thinking, and how students can deliver their solution. In order to do so, we designed a curriculum in such a way that there are lots of project-based courses. Maybe you cannot see clearly, but there are here and there are like Design Project 1, Design Project 2, Design Project 3, and so on and so forth, and which has lots of credits, at least 5 credits, which is like a lot of work. In those courses, in the project-based courses, there is of course a continuous need to prototype the product or prototype the physical prototypes, and 3D printing helps a lot with this within a acceptable time scale, because normally in the past, when product design students wanted to create like prototypes, they had to rely on conventional manufacturing methods, which may take quite long. But nowadays with 3D printing, it's really easy, it's really straightforward. And what I will show you later, it allows design iteration, which we also want our students to experience this experience of having design iteration. So the first example here, what Design Project 1, the course Design Project 1 is 5 credits given in the second year, 4th semester. The students here, they have to master at least one 3D software. It can be anything, it can be SolidWorks, can be anything. We didn't really have strict requirement of which software to master. It can be anything. And then in the first part of the first week, we actually introduced the themes, specific themes or design challenge to the students, and they have to identify their problems, define the problems, and ideate their solutions. And then so they design the solutions based on the introduced challenges. And then we also, within this course, we collaborated with other study programs, which is computer systems engineering. So both study programs, they work together. The students from both study programs work together to develop a solution, a physical product. And of course, we realized the prototypes using FDM 3D printers. So this is these are several examples. So we used our prototyping lab. It has several 3D printers, Creality 3D, I think 3V2. And then maybe this one here is autonomous vacuum cleaning robots. So computer system engineering students are really good at using, Arduino sensors and everything. Product design engineering students, they are required to be able to realize that within let's say a real product or physical product. And there are lots of challenges with realizing this product. For example, how to fit all the components inside, because it has like small fan inside. So this kind of thing requires lots of iteration, lots of design iteration. And 3D printing really helps a lot, because students can learn hands-on experience, they can practice hands-on experience troubleshooting and everything, they do it on their own, of course supervised, but at least they have these opportunities to be resilient, to be persistent in delivering this solution. The second one here, bottom right corner, is I think this one is a product for detecting crack for glasswares. This is based on real problem in our lab. Students, you know, they broke glasswares a lot. Sometimes when it starts detected, a crack already appeared. They didn't realize, and once it's used, it just cracked immediately. So I think this is a good example of how they see in real life what problems are there and provide a real life solution. So here uses of rotating. So the idea is to put the glassware on those two rotating shafts there, and then it was 3D printed also in combination with other materials, also like I think it's acrylic plates. And here, this is more like fun games. If you know the tag game, so you chase your friends, you touch the plate there, and then you get a score. So this is also very interesting illustration of how they can develop products using 3D printer. So in the next one, the computer-aided engineering, I'm going to show you maybe the main thing here is we use topology optimization and generative design, because this is like a hot thing in CAA, especially in Autodesk Fusion 360. We can use these features. If we have education license, we can already use these features, topology optimization and generative design. The idea is, okay, they know they can use these features to, let's say, reduce materials usage, reduce cost, and the idea is also to have students, allow students to redesign a product, or at least to reimagine their design, to give it an alternative, to make a product alternative which is more effective and efficient. So this is the typical, this is one example. This is the typical procedure in topology optimization. This is a simple example of cell phone stand. So this is the initial design. By topology optimization, they can reduce the weight, but still maintaining its main function, which is to withstand the cell phone. The next one here is, this is for laptop, and also this one is for flower vase. So it is simple products, but using topology optimization, they can really use this feature to develop more efficient or more efficient solution which uses less material. The next one is generative design. So this is a guitar stand, the guitar hanger. This is the traditional design, and then they develop a new design using generative design here. And also this one here is for bookshelf, inspired by garden bench. But for here, this is only rendering, so it did not continue with the prototyping itself, because this one here actually they designed using metals. We don't have metallic 3D printers. And this one here, I think it's polymer, but I think the students did not prototype the final product. So it's only rendering or computer design. This is for final project. It's a device to help people with low vision disability, because there are people with low vision who have problems in supermarket, for example. So it uses computer vision to recognize an object, and it will make a voice like "Teh botol sostro." The price is 30,000 or 5,000 rupiah, something like that. So this is also prototyped using FDM. And this is another example for final projects. Maybe I will just go to this slide. So the key takeaways in teaching and learning is 3D printing is essential. At least FDM for higher education for universities is a must-have, because it's already really affordable nowadays. With $200, $300, we can already get desktop 3D printers. Of course, we have to keep up with advances relevant with AM, for example, generative design, topology optimization. It's a ready feature in Autodesk Fusion. 3D printing boosts creativity and collaboration. I've shown you the examples. It allows design iteration with an acceptable time scale. and also introduce real-life design non-linearity with iteration. So it's not a linear or sequential process, but at some point you have to iterate or you have to change your design, and it can be allowed using 3D printers within acceptable time limit. And also it stimulates persistence and resilience. Students do a lot of troubleshooting, so yeah. Okay, the next one is the second case study, which is community service. So we did community service programs at vocational school, where we teach vocational school teachers how to use 3D printers, because some vocational schools, I think many vocational schools do not even know what 3D printers are. So I think there's a gap in that sense. So we performed the program at SMK 1 in Cianjur, Regency, and this is the process that we do. So we gave them a workshop on human-centered design and 3D printing. And then after we trained them, we trained the teachers how to use 3D printers. They work independently in a group, in a mini project to develop their own products, to develop their own prototypes. And after that, we gave them a second workshop on project-based learning, where they also present their results there, and then they do some reflection and evaluation. So here we have improvement. We gave them initial test. They didn't know everything, so the score is very low, 41%. And then after the end of the workshop, there's improvement of their knowledge on 3D printing, around 30%, which is quite okay. So this is some activities taken in photograms. We used, this is $200, around $200 printers, FDM Creality, which is portable, so it's very practical. So those are the examples of the prototypes developed by vocational high school teachers. They didn't know everything about 3D printing before. Within 1 month, they could build this, which is very exciting for us, actually. So the key takeaways for vocational high school is that there are gaps to fill in terms of adopting AM and 3DP. I think it's easier to find 3D printers application with at higher education institutions, universities, but not as much in vocational high schools. There are also various opportunities in leveraging 3D literacy. There are actually interesting programs at vocational, for example, agriculture, fashion design, hospitality, culinary arts. They express their interest in using 3D printing. Actually, for agriculture, for example, they adopt IoT, and they want to make an enclosure for their systems, their sensors, so they need 3D printers. In fashion design, for accessories, hospitality for the models of souvenirs, culinary arts, also models for the food, and so on. So university support through community service is quite feasible in this sense, and we got positive feedback actually on the practical benefits from the teachers. They illustrate how they benefit by learning new applications and also gaining hands-on experience with 3D printing technology in the hope that they will also teach this to their students. But I have to highlight that we need strategies to ensure the program sustainability and also the long-term impact of this program. So with that, I would like to end the presentation. I would like to acknowledge my colleagues and students at UPM, of course, the grant awarded by the ministry, and also our partner at SMK 1 Pacet Cianjur. Thank you very much.
Thank you, Pak Zaki. I have question, but I think I'll open it first to the floor. If there is question for Pak Zaki, I think this is a very exciting case study for AM. I agree. It's exciting to see the high school case. Any? 2 minutes? Me? Any? Oh, yeah, please.
Pak Zaki, I think congratulations. I think this is really something that we should bring, and disseminate to other higher education institutions, because it is really important also for our students to be able to work with their hands. So I was really impressed with your lab. I think maybe in some places, I don't know whether in Bapak place there is a idea of maker innovation space, Arif. So this is, I think we could, talk about more. 3D printers more affordable. Some of our alumni in Bandung produce this. So we bought their products to use for our students to make this in the design project, final year project, and even we are thinking about Pak Satrio for first year students, right? For next year, in our course of Introduction to Engineering and Design, we will, introduce human-centered design, and then design thinking, and then of course some simple stuff that they can make their own. So I think I really appreciate that. Thank you. So not a question, a comment.
Other question? I'm a bit more excited about the generative design. I mean, so yeah, I mean, can you tell us a little bit more about, because I mean, obviously it involves some kind of simulation, some kind of optimization.
Well, actually, it was based on my personal reflection on the course itself. In the beginning, the first year when I gave the course CAA, it's all about finite element methods.
Yeah.
The first year, the students at that year did not enjoy it much because it's all mathematics and everything.
Yeah.
But once I came across this article about General Motors,
Yeah.
adopted this approach, and I learned that it can be done using Fusion 360 and stuff.
Yeah.
Interesting. So that's why I try to embed that aspect into the CAA course. It turns out students really enjoy it because they can
That's
really
cool.
see how computers,
Yeah.
maybe it's AI,
Yeah,
it's
yeah.
algorithm, like imitating biological processing.
Yeah. But maybe you want to define the generative design, because maybe some.
Means that we define the design space and constraint, so we don't define the final shape and let the computer do the calculation and adopt some kind of an algorithm that mimics process in life that results in efficient and effective structure. So that's why the typical shapes obtained using generative designs are, we call it organic shapes. It's not geometric shapes. Geometric shapes means like round, circles, and everything, but organic means like branches, fish branches, seashells, lattice structure. So that's why this shape here is something like this. This is like tree branch. It's quite interesting to see how GD can give us quite unique shapes as compared with traditional shapes like that.
Cool.
But here, we still are quite limited with the tools. The idea is this is metal material still, but we didn't have access to that. So I told the students, okay, just make the rendering of shapes.
All right, Pak. Let's continue our discussion in Jimbaran during our banquet. So we need to move on. So the next speaker will be Professor Ari Wibowo from Institute of Technology Bandung, Indonesia. This title is actually the title I made up because until the last time I still haven't received anything from Pak Ari Wibowo. Pak Ari sudah sorry. Okay, Pak Ari. So yeah, the title may not be this title. So please, without further ado, maybe the floor is yours. But we are excited to hear the development of AM maybe in the materials engineering, because I think in mechanical and aerospace faculty, Prof. Andi Mahyudin has already shared. So maybe in materials engineering, Pari, you can share a little bit more. Go ahead, Pari.
Okay, thank you very much, Professor for the introduction. Yeah, after seeing the presentation of Dr. Zaki, I think I'm a little bit make a different presentation. So in here, actually, we try to introduce the additive manufacturing to our students. In our class, we all use several movie that we want the student know that actually 3D printing is something like a future game changer for the future, because the additive manufacturing considered as the future manufacturing technology, because they provide rapid prototyping for complex structures. So it is kind of, let's say, today we have an accident in the railway, and sometimes there's a problem with the railway with a lot of complex spare part, and if the spare part is missing, the locomotive will stop, and we need to wait. And sometimes the railway need to store a lot of big storage, so to store the spare parts. So in here, if we use the additive manufacturing, we can prepare the spare part, yeah, faster, and even though the structure is complex, we can prepare it faster. And right now, a lot of aspect in our life will kind of the interactive with the additive manufacturing. So it could also the for the industrial point of view, this additive manufacturing is interesting because it can reduce the manufacturing time and number of parts significantly. So that's why in our class we try to introduce, you need to know about the additive manufacturing. Why? Because the additive manufacturing could be a game changer, and maybe in the future you will be involved in this game changer flow. So we try to use several videos to attract the students. First, we use the video from YouTube. So why we need to know about the 3D printing method? Because it could reduce the number of part and manufacturing time. So this is we take the video from the Symposium, and take this is about how to prepare the engine. So
This is the world's largest
sorry.
3D metal printer. It was built by Relativity Space, a startup that aims to print an entire rocket, including fuel tanks and rocket engines, in just 60 days.
I'm like looking in.
Wait. Let me use
Inside a 3D printed rocket that is actually going to go to space. This giant hunk of metal. It's unbelievable.
This video is sponsored by Omaze, offering you the chance to win a trip to space. More about that at the end of the show.
There's a lot of UV coming off.
Because the video is about 16 minutes, it's not suitable for content. So let me faster to the most important part of this video. Okay, this one.
Started using metal 3D printing over a decade ago to construct small complex parts, for example, the injector.
That is the most important part of any rocket engine, where you're basically got to take a liquid propellant and turn it into a fine mist that mixes really rapidly. And those have actually been transitioned to 3D printing all over the industry.
Traditionally, something like this, it's a rocket engine injector, so it mixes liquid oxygen and liquid methane propellants together, and this is what actually produces all the fire and flame that is in a rocket engine. Traditionally, it would be over 1,000 individual pieces, and it would take 9 months, but here we're 3D printing the whole thing in one piece. It takes 2 weeks, and it costs 10 times less.
So, sorry. So this is the most important part that we try to introduce to our students. By using the 3D printing, we can reduce the normally the traditional section need a lot of spare parts. Using 3D print, we can only need to prepare the one part as a single part in here, and by using this new technology to manufacture, we can reduce the traditional manufacturing that normally take 9 months to become only 2 weeks. So apparently we can reduce the cost of the manufacturing in here to become more cheaper than the traditional one.
One of the big benefits of 3D printing is reducing the number of parts. Have you ever thought about how inside a rocket's combustion chamber, it gets really hot, up to 3,500 Kelvin? That's hot enough to melt virtually any metal. So how do the combustion chamber and rocket nozzle not melt? Well, the answer is they're cooled by passing the cryogenic propellants over them.
On the space shuttle main engines, I love to talk about them because inside those engines, it's hot enough to boil iron. On the outside, you can freeze stuff to the exterior of this because you're running liquid hydrogen through these things. But to make those, you basically had to take thousands of very small pipes, and then you would form them into the shape of the combustion chamber and the nozzle, and then you would braze weld them together. And this was a ridiculously labor-intensive task. You would have 1,080 individual pipes running up the side, all having to be welded together to make the combustion chamber and the nozzle on the space shuttle engines. So you can actually 3D print these things.
This is a rocket nozzle being 3D printed, and you can see the channels for the cryogenic propellants being printed right into the single part, instead of having to add 1,000 pipes on the outside. Smaller parts like these are typically 3D printed using metal powder and lasers.
You can see the cooling channels are all being built as the one piece. So this is a nozzle. It really just lays down a layer of powder that's about a 20th the thickness of a human hair. So it's really, really fine layers, just over and over and over and over relentlessly for probably about a week or so, and then out comes the rocket nozzle. All printed as one piece. It's way cheaper than traditional. And this has 4 lasers going at once. That's amazing. I get asked a lot, well, aren't 3D printed metals not very strong, or how can it actually work? But the printed materials are stronger than they would be built traditionally. Actually, it's counterintuitive. It is, because
it takes too long to run the video. So I will change to the second video that normally we show it to the student. The second one is the reason why the 3D printing, because it can print the complex structure. This is the bone, and the bone, there's a cortical and the trabecular. The trabecular bone is quite a complex structure, and we need to make it precisely. So using the 3D printing, we can mimic the structure precisely. So please allow me to run the video. Okay, and the other one is we try to emphasize the student to make a dream, because in the future maybe everything starting from the dream, and sometimes the current technology is kind of a dream in the something like a dream in the past. So kind of we have a video call, we have something like this. This is kind of the dream in the past. So also we try to introduce in the future organ donation is become a limit, and it's very difficult to get the organ. So 3D print can be solved to this problem, even though this is not still not reached yet, but in the future this is running.
Donors are difficult to find, and what we want to see is trying to be less dependent on organ donations. So with 3D printing, the capabilities to be able to generate organs which are acceptable to the recipient are much larger. But we're not there yet. We are moving towards that direction. 3D printing in healthcare could be defined with two different applications. One is from the model's perspective, basically models that you can literally print into a particular shape and then adjust to the patient. We have certain examples where we see that already starting. So the dental industry sees the printing of crowns and invisible type of braces that could be printed for the customer in the office. And the reason why this is a method that is fairly economical, especially for the patient, is that you do a scanning of the impressions of that patient and then are able to modify in an electronic file what you would like those final state of the teeth to be. And then you're able to replicate multiples of them in one platform. And then there are less visits to the dentist. In using 3D printing for prosthetics, they help from the perspective of being customized and fitted to the stump where the former limb was located, and they're made out of off-the-shelf polymers, so they're not too expensive. From that perspective, it's also cost minimizing in comparison to traditional prosthetics. For example, in the use in pediatrics, the patients are in constant growth, and the cost associated with that fitting will be lower. It also will be a rapid turnaround in comparison with traditional fitting of prosthetics. The second application is bioprinting. The tissue engineering market in relation to 3D printing or bioprinting is expected to have approximately 32% growth in the next few years. The main difference associated with a bioprinting operation and a 3D printing operation is the use of bioink, which is artificial or it could be natural materials, and the mixture of those with cells. When we say artificial, think about polymers, plastics, and natural could be lactic acid proteins. From the perspective of drug testing, bioprinting could offer flexibility in terms of cost efficiency. And what I mean by cost efficiency is animal testing. Animal testing is fairly costly and does not replicate what the interactions of the drugs will be with the human. So having a platform with 3D printing where we're able to replicate what the human tissue would be, provide us one, repeatability for the drug testing, two, lesser costs associated with the drug testing. A lot of studies start with mice or rats, but then to be able to prove that it's truly efficient, you have to go with larger animals. And you have to take care of them during the process of drug testing, and it's costly. And with bioprinting, it does provide you a platform to be able to do drug testing without the use of animals.
Okay, so we try to emphasize to the student that 3D printing is very soon. So this is kind of the future, and maybe you will see something like future technology and a lot of technology around us is already approached by the 3D printing. So in here, beside the introducing of the 3D printing technology to the student using the video. We try to doing several activity in the related to the additive manufacturing, and let's say we can divide it to function, filament. This is kind of raw material, and numerical. As Professor Andy mentioned that in his presentation, discussion about the filament, about biodegradable and recyclable filament by Dr. Mardiati and Dr. Stephen already highlighted intensively in his presentation. So maybe in this case, I would like to introduce two activity in our department using the low cost or low budget 3D printing machine and numerical study in composite that prepared by Dr. Dito Pullman. So, as we know that previously we published two paper using 3D printing with the polycaprolactone with the silver nanoparticle published in Molecule, and the latest one published in Material Advance. We use 3D printing because offer this method offer precise technology, morphology and dimension, high accuracy and good stability for complex geometry. However, in our case, we use high state-of-the-art 3D print facility, which is costly more than 200,000 US dollar. And the problem is we cannot use this machine in our lab. So we think that is it possible to prepare this composite polymer, the polymer with the silver nanoparticle stuffer with using low budget. In here we buy the machine with very cheap, about 200 US dollar. This is for a student to learn how to use this, and is it also possible to use this machine for advanced something like this? So this is the material that we use. We prepare the silver nanoparticle based on the UXPs. We can see this is a broad peak at around 400 degrees, 400 nanometer, which is a characteristic of the SPR effect of the silver nanoparticle. And also based on the XRD, we can see that the sample that we prepare actually a mixture of the silver and silver chloride nanoparticle. And then we try to mix, we try to combine with the polymer. However, if we want to use this, if we want to use this machine, we cannot prepare the PLA and silver nanoparticle, because this machine normally for the commercially available filament only from pure polymer. We cannot use something like a mixture. So if we want to make a composite filament, we need to prepare the filament first, and then using as the feeder for this 3D print. So in our case, we need extruder and winder as additional equipment. So instead of mixing in Manchester, we just mix the polymer with the silver nanoparticle and then go to the 3D printing machine. In this case, we need to prepare the filament. So we use the extruder, we melt it in here, mix it, and then melt it in this extruder. And the extruder in here is rolling using this winder to make a filament, and then this filament is fed to this 3D printer. And this is the result of the filament based from the extruder in here. This is the polylactic acid filament using the pellet, and then we can prepare the filament. And by the addition of the silver nanoparticle as the concentration 0.1, 0.3, and 0.5, we can see the filament become darker. However, kind of twisted. The filament is kind of twisted, so the result is not so good. So You can see this is the scaffold after the filament was fit in this 3D print, and this is the result of the scaffold correlated with this the filament color. By increasing the concentration, the scaffold become darker. However, as you can see in here, this is the SEM. The pure PLA is quite okay. We use the PLA pellet and then melt it and use the extruder, and the result is quite okay. However, if you use the a mixture of PLA with the silver nanoparticle, kind of pour in here unnecessary or unwanted pour in here occur, and we didn't know exactly what happened to here. However, from the pore size point of view, we can see that the pore size is higher than 300, which is preferable for bone cloth, and this is quite beneficial for diffusion of nutrition. And according to the wettability is important because when we decrease the contact angle, we can increase the cell adhesion. So wettability is important parameter, yeah, in tissue engineering. And the addition of the silver nanoparticle, we can reduce the contact angle, which is this is consistent with the previous result that published in molecules. And this is as the conclusion of our work. Maybe we will skip it. And the second one is from the Dr. Gito Pulungan. He used the numerical study about how to study in the composite. And as you can see, the carbon fiber reinforced polymer is significantly increased in here for the aircraft, and we need to define demand to improve the adhesive joint toughness to accelerate and the accelerate the crack propagation. So in this case, he used the model validation and bridging development. This is the finite element with the insert of thread, and this is a comparison, and this is the crack propagation, and this is actually not my work, so I need to read it. So the bridging mechanism in here, physical phenomena that occur at various loading points, and also the introduction of the insert to adhesive layer here lead to the formation of bridging, which is effectively arrest the crack propagation in here. So that's all for my presentation.
All right. Thank you, Pari. Let's give applause for Pari Wibowo. I think we are kind of pressed in time, Pari. So I think we'll take note if there is question for Pari. But we'll move on to the next presentation. It's actually from our program in MMET in Oregon Tech. Thank you, Pari Wibowo. Let's give applause again for Pari. Maybe you could help take over because this is our duet.
Right. I think it's.
So I'll start a little bit, and then mostly you Brody will present.
Yeah.
All right. This is mostly we share our experience in our department in Oregon Tech. Well, as Prof. Andi has already left, it seems. But as Prof. Andi mentioned, we do have maker space in Oregon Tech. It's actually quite a large facility with a lot of 3D printer, different kind of polymer, even some ceramics as well. And we do already have like design projects that many faculty members in MMET try to infuse more and more AM into our design projects. even students themselves, they have some government funding that if they want to buy 3D printer, like home 3D printer, for like $300, they can just apply to that government funding website and actually get for them at home, not even like in the lab. Personal, yeah. So I don't know, but anyway, I think in this, I probably just talk a little, 1 or 2 minutes, but mostly I want to let Brody, the student himself, share a little bit about what we have done. I think in particular in one of the class that we just finished actually 3 weeks ago. In that class, basically I try to infuse it into my fracture mechanics class, which is kind of like if you follow a little bit of what my talk and also Dr. Mark John talk, I think you will get the idea that with 3D printing, we can actually create a certain path of fracture that is favorable to us according to the geometry of the design of the component, for example. So that's now become possible. I think that's probably one of the examples that Brody might. But I think this is sort of like a few slides that I keep providing it to students. The fact that I think we sort of like in mechanical engineering, we learn about design and manufacturing as in so but now with the additive manufacturing, a little bit of the way we do design and manufacturing in industry, as well as the way we teach it as an academia, might need to change. And that's the concept that we have on design for additive manufacturing, or ISTA-AM. Next. Obviously, one of the examples that I think we all have heard a lot in this conference, especially design with lattices, same structural integrity, much lighter, safe material. Next. I think we all have seen this potential and limitation. I think a lot of the discussion have actually touched on that. I think one of the things that I think haven't been discussed much actually in this conference is the fact that I think one way that additive manufacturing has come into real changing of business models is in the remanufacturing vision. And this is something that Singapore, just basically an example of turbine blade, and turbine blade easily have wear, tribology problem. And what they do right now is when it is, well, this is actually an exaggerated example. It's like, but if you have a wear and then if it is already too much, then what they do is they have to replace. And what they do is they basically scrap the whole material. And turbine blade is actually something that is always made out of a very costly material. High nickel alloys, super titanium alloy. So one of the, and this is actually part of green vision that I think we keep hearing from Professor Satrio Sumantro Bojonegoro, Dr. Fauzan Aziman. The idea is that now, well, in bahasa Indonesia is tambal gigi basically. Ini gigi yang udah keropos ada ditambal gitu ya, dibanding dengan giginya kita cabut, terus diganti dengan gigi baru itu. So this is the idea. Like it's a dental thing. How is it? Well, I think it's if you have like your tooth already corroded, and then you have to create a crown. That's basically to replace this part, right? So this is actually, at least in Singapore, Changi, they actually already will be implementing this because obviously airlines, it will be a cost saving for airlines. if you have remanufacturing. Actually, Singapore, they have probably about the only country in the world that I've seen a center for research in manufacturing and remanufacturing. So the remanufacturing vision is basically for repair and only a particular laser. It's not laser powder bed fusion. It cannot be used. LPBF cannot be used for this. It has to be a certain 3D printing of metal, which is directed energy deposition. What would allow only addition of material following this contour of gigi yang tongkos tadi. All right, so easily I think two industry that will probably create that will have additive manufacturing infusion will be aerospace, simply because it's the most extreme part of engineering most of the time. And I think the next will be biomedical. At least that's what we've seen, sort of like the most potential for additive manufacturing. DED is actually one area of research that I specialize, and I think we in Oregon Tech we have the machine, we have the expertise, we have the quite a bit of experience and publication, especially in DED. I think we have one more paper coming out, right, Pasaki? I'm sorry. We actually have like a grant together between Pasaki and Binus and us, me and Tim in Oregon Tech, on DED, on basically the remanufacturing vision. I think I'm going to skip this one. What I'm going to do next is basically just introduce what Brody will probably talk a bit more. I think I'm skipping this one. Yep. And I think Brody will tell a bit more. Will tell you a bit more about how at least his experience in having classes that is we try to infuse more and more and more of AM into all classes.
Yep, so this will be a bit of about our that project for the fraction mechanics class. These three were my group members, and this presentation is about additive manufacturing in education at Oregon Tech. So in the fraction mechanics class, it's very detailed in fracture properties for various types of materials, and a big part of it is a term-long project. Either a literature review where you look at where you analyze an existing fraction mechanics case, and then there's also some groups do testing and of some simple case that you see would be useful. So the first part is you do a proposal, sort of the purpose of your investigation, what you think is going to happen, your hypothesis, and then what your next steps are for the project as a whole. And some projects from my term, from other groups, were there was one on the fraction mechanics of nanoscale silicon features, and on the de Havilland comet failure. For our group, we were focusing on comparing additively manufactured to conventionally manufactured ceramics. Our goal was to use an FDM 3D printing process with sintering for additive manufacturing, and then use a mold and some ceramic paste for conventional manufacturing. There's a lot of applications for ceramics in high-performance applications. One very common one is turbine blades, as the incredibly high temperatures they experience make ceramics a really good fit if they can be manufactured properly. And so our hypothesis for what we were testing was that whether layer interfaces would deflect cracks. Because we've seen how if an interface has a low surface energy, it can be preferential for the crack to go in that direction. And then our testing was going to be basic tensile testing, but with a predefined crack for testing propagation. And so in the end, our testing didn't work. We were able to manufacture green samples, but the furnace we used for sintering couldn't get hot enough to properly sinter them. Though one thing we did notice is that some of the features from the printing, the voids from the layer lines, were still apparent. And so then for our literature review, we went over many of the different methods for ceramic additive manufacturing, including FDM printing, which we tried to do. There's selective laser melting, binder jet printing, and ceramic on-demand extrusion. We go into more detail with these in our real presentation, but then also slip casting as a example of conventional manufacturing. We look at the literature to analyze the fracture toughness of additively manufactured ceramics. In this case, we chose zirconia, as it was had a lot of information with it in the literature. And we actually found that the fracture toughness of additively manufactured samples were similar to conventional zirconia. And then also that the layer orientation, at least in the testing here, which I believe was SLM actually, sorry, that's a typo, but that they were similar. And then looking at the different methods for crack deflection, the one we were trying to use was having manufactured voids. In this case, this is a study from 2023, which used PLA plastic and achieved crack deflection. We then looked into other methods for crack deflection. The two most notable ones were biomaterial layered ceramics and also an advanced lattice structure that was able to deflect cracks. With more details here. So the layered ceramic had two separate ceramics in layers. They had internal stresses which made crack deflection very preferential, and it was in the study was manufactured using slip casting, but based on our understanding at the time, we were confident it could be manufactured with FDM printing if ceramics could be. Then we also looked at some of the math behind it, how you would approach deciding whether a crack would propagate or not. Then there was also the advanced lattice structure example, where they were able to sort of define crack propagation geometries. And so our conclusion for the project was that manufactured interfaces could allow for control of crack propagation, and that changes in material density can be controlled with additive manufacturing to create structures that we want, and that FDM printing does have the resolution required for the for the features that need to appear. And so I think a really big part of additive manufacturing and education is building it into the curriculum, and not just having it in additive manufacturing class, but including all of the relevant knowledge, like how fracture mechanics might be different in additive manufactured components, how you might design a part differently, and just including those in the curriculum because that's really what it is. It's going to be a large part of the future, so it needs to be a large part of our curriculum. And then also, additive manufacturing can allow for a lot of novel solutions to industry problems, as we've seen across this conference, and that people who are getting educations need to have the experience with additive manufacturing to be able to solve those problems effectively. And that's it.
Let's thank Brody, and maybe you have one question, short question for Brody for his experience as a student in OIT. No? All right. So I think let's thank again Brody. So next, we will have again sharing of experience from AM program in Universitas Trisakti, Indonesia. Oh yeah. Yeah, I think it could be just maybe a sharing of your experience of
you don't have any presentation. We are also trying to wrap up the session, hopefully before 6:30. So any 1 or 2 minutes.
Short time. Okay, thank you, Pak Arif. So I would like to share some information regarding AM in Universitas Trisakti. So especially in our Faculty of Engineering or Fakultas Teknologi Industri. So we have two 3D printer in our department, Department of Mechanical Engineering, and we have three 3D printer in our Industrial Engineering department. So we use these 3D printers for some for final project of our students, and also for commercializations, because our Faculty of Engineering, we've been trying to have some income from non-students income from our labs machines or activities. So we like, if there are some order to have or to make some components, we can use our 3D printers. So unfortunately, I cannot show you some of the projects or some of the research, because some lecturer or faculty staffs could not come to this conference. So we have like Dr. Sali Cahyati. She is an expert in manufacturing and also in 3D printing, but unfortunately she couldn't come. And also there is Dr. Triono. He's an expert also in manufacturing. And actually we have also our head in one of the research center in our faculty, Patono maybe. So that's our expert also in manufacturing and construction. But actually our faculty, with the supervision of our Dean, Bu Rianti, we have some enthusiastic plan or commitment to have some AM projects. Because in the last 6 months or 1 year, we have some webinars or workshop on 3D printing. We have some expert from US and from Germany. We been discussing with our faculty staffs about 3D printing. And I myself, I've been trying to make some proposals to Faculty of Engineering, to our Dean, to buy some 3D printer or metal 3D printer. So I hope maybe in this year or next year, next year, we can have some metal 3D printer. So our faculty staffs, our lecturer can have some research more extensive in this AM. So that's all that I can share, Pak Arif.
Thank you, Pak Desmond. The last piece will be another student sharing experience from OIT, from our department. Ms. Leslie Landon will share a little bit, I think maybe just 5 or maybe at most 10 minutes, about a particular research experience that she's working on a project with me, actually. And I think maybe more importantly, we want to hear from the student point of view, how the research project perhaps has help enrich your education experience in as an engineer. While they are setting up, please don't go yet, because we will have the best student paper announcement and presentation of the award after this, and then we'll move on to the transportation for our banquet.
Try and make this fast. Good afternoon. My name is Lacey Landon. I'm an undergraduate student at Oregon Tech. It's a weird one. Yeah, thank you. So today I will be presenting the fabrication of novel 3D anode battery design for next generation lithium ion cells as part of MMET design and manufacturing projects. This project focuses on the additive manufacturing of building a 3D anode that enables a lithium ion battery to have a higher charge density and longer life and efficiency. I will also be discussing how this has impacted my education for the better. So our problem statement is 3D nanostructure anodes, they've been done, but the existing manufacturing method is quite expensive. Current method being graphite that's been heavily processed and baked into a copper foil. Next slide, please. Next slide. And next slide. For the anode, we want it to be faster charging and more efficient. So surface area, material, and structure, all very important components of this. The surface area affects how the lithium ions can insert into the anode and pass between the layers of carbon atoms. The material is important to keep the shape of the anode in place during the charging and discharging, and graphite is a common choice for this due to its fairly large space between the layers of carbon atoms for the lithium ions. However, it is quite expensive. The other materials, such as transitional metal oxides or alloy anodes, may use redox reactions and displacement reactions, respectively, to accomplish the same process. The structure of the anode allows for more or less surface area of the lithium ions to insert into the anode and more open space in the electrolyte solution to pass through during charging and discharging. Next slide, please. So we had a lot of research and preparation for this. Going into this, I had no idea what electrospinning was or how to do it. So to begin, we utilized Dr. Raul Sai's paper titled Copper Oxide Anode Electrospun Fibers with Battery Cell Testing for Performance as a starting point to get familiar with the process. We replicated this paper process while using materials and parameters of another paper of Dr. Raul Sai's. And that was producing nanofibers of polyacrylonitrile dissolved in the methylformamide between two parallel plates and a matrix material in a custom-made 3D printed collection plate that was designed and manufactured by a student who has since moved on, Ronnie Roundtree. But he designed a custom 3D printed collection plate that also had interchangeable plates for a stand that was able to rotate with minimal horizontal movement between the plates to allow for our orientation of the fibers. So initially during our replication, we used a helicoidal 15-45 degree orientation shown in the SN image here. Our average fiber diameter was around 1 micron, and this particular sample was 13 microns thick. This is just an example of how our line fibers will be in a 0-90 degree orientation in our final battery anode. Here's just kind of our setup of both the replication and optimization of our fiber diameter. And this was using the polyvinyl alcohol as our matrix. So electrospinning as an additive manufacturing technique reduces costs and enables synthesis of nanoscale polymer fibers by using an electromagnetic field between the stainless steel needle and a metal plate. In this case, two parallel plates and a needle with a high voltage source attached to the stainless steel needle. We decided to start with the carbon fiber for simplicity's sake, as well as a aligned fiber orientation as mentioned before. However, we decided to use the polyacrylonitrile with a copper foil matrix over the collection plate that was carbonized at around 1800 degrees Celsius in an inert argon gas tube furnace. material fibers into carbon fibers as the temperature increased, starting at 900 degrees Celsius. During this process, we had a few limitation issues with the foil and compatibility of the matrix and the fibers. But they didn't adhere as we expected them to during carbonization and resulted in a messy tangle of carbon fibers. So going forward, I have a lot of homework to do on the different types of organic polymers we can use. Perhaps one that's more attractive to the copper foil, i.e. needing more electrons, or maybe a different matrix material that would sublimate entirely during the carbonization process, or be capable of being incorporated into the battery anode. So as we progress through this project, there's a lot more for me to learn. I'll plan to dig deeper into the chemistry of the materials we're using and do additional literature research to determine possible alternatives for materials or processes to remedy the issues we've experienced. Our overall goal is not carbon fibers, but rather silicon fibers, which comes with its own set of challenges. But again, we need a basic groundwork to get me started, as this is all very new to me. Prior to joining this project, as I mentioned, I had no experience. I learned a lot about electron microscopy, the electrospinning machine, and definitely a lot of troubleshooting occurred. I learned a lot about conducting research properly and proper chemical safety practices. And since beginning, I've spent countless hours, especially over the summer, with these machines, and have recently even begun leading trainings on how to use them to pass on my knowledge to other students and even some faculty who were unfamiliar. And as many of us know, mechanical engineering majors in undergrad, we take chemistry, material science, physics, and thermodynamics. But a lot of stuff we don't learn in class, which has recently been integrated more, is practical applications of the concepts we're taught and properties of the materials we're learning about. I've learned how to utilize the chemical and mechanical properties we're learning about and use those in practice and bending them to my specific needs for a specific goal. Gain insight into what I'm learning in lecture is relevant and how to utilize my knowledge effectively. My education has become more valuable having participated in the additive manufacturing research. And just to kind of wrap this all up together, I would like to offer a question for all of you to think about, especially as educators and researchers. What to you makes an education valuable? Thank you.
Thank you. You make my eyes teary. Such a music to my ear, right? Thank you, Lacey. Maybe there is a question for Lacey. If not, I think let's move on to our final event. Okay, so we are going to announce the winner for the Best Student Paper Awards. But before that, let me explain a little bit about how we judges come up with the winner. So there are 11 students that are qualified as student papers. Mostly the qualification is that it has to be submitted by the student, the paper must be submitted by the students, and then must be presented by the students. It could be online. I think there is one student paper that is actually delivered online. It's okay as long as it is delivered by the student. So there are 10, I think, that are qualified, and then each of the student paper are judged by at least 3 judges. The judges are mostly people from the chairs. So it's me, Professor Wang, Pak Endang, also from scientific committee, Pak Zaki Zaldi, but also a few other people from keynote speakers. I think Professor Sukamoto, I think, probably did quite a few judging. But basically people are also hubungi, I think. So a few people that are in our organizing committee. Basically, at least every student have 3 judges that are actually in your presentation and give scores that are. So we have a criteria, 2 main criteria, and this is actually not a criteria that is
real or anything is a normal criteria in any scientific conference or for best paper students. First, it's always about the paper itself, the scientific merit, the novelty, the originality, the broader impact, the contribution to science. So it's a normal thing. And then the second criteria is about the delivery of the presentation as a student paper. So it's usually meant about whether or not it's complete, the presentation is complete, whether or not the delivery in terms of the English language, in terms of the systematic of the presentation. So those are the two main criteria. So these are the same two main criteria that is used in any best student paper award in any international scientific conference. All right, so with that, so our first, maybe let's start from the number 3. Okay.
Don't get the wrong list. Students will chase you out.
Roll drums. Roll the drums. All right. Number 3. So it is a bronze award. Is student I Made Bagus Aditya from Udayana University. I think maybe we can just do the presentation right now, or Pak Hadi, please. Are we ready with the certificate of appreciation? I think we can do it like.
Okay.
Yeah. And then I think let's Imade, Imade Bagus Aditya from Udayana University. His presentation is prosthesis smart arm based on object detection with you only look once YOLO and hand gesture with recurrent neural network RNN. Okay. It's an AI paper. So it's actually not an additive manufacturing paper. Maybe we should reconsider. I think as we mentioned, this is not only additive manufacturing, it's actually also technologies that are enhancing manufacturing in industry. All right, so I think it's so the award is actually $200 for certificate and placard. So I think maybe we can. Good job. Yes. You are it. Maybe please still stay on the podium. All right. The silver award is won by Mr. Brody Miller from Oregon Tech. His paper is structural modeling and fracture mechanics of novel 3D lattice-based structure for unmanned aerial vehicle application enabled by additive manufacturing. Oh, by the way, I haven't mentioned, but when we did the judging, none of us judge our own students. So he won not because I judged him. The three judges are always judges that are not their professor. All right. So. Okay, so for silver, it is $250. Certificate and placard. Finally, drum roll, please. Thank you. So the first winner, gold prize for International Conference on Science, Technology, and Application of Additive Manufacturing 2024
is Mr. N.M. Yudawi Sastra from Bandung, Indonesia. His paper is a numerical prediction for relative modulus of strap-based gyroid lattice structure. So the gold winner is $100 certificate and placard. Congratulations. All right, speech. All right, I think is there any other?
The award is actually being available or provided by courtesy of the Toyota Motor Indonesia. Unfortunately, they couldn't join now to see to hear this.
But yeah, quite a bit of actually of what we have done, what we can do in our conference is by courtesy of Toyota Motor Manufacturing Indonesia. I think this is something that we would like, if possible, to continue. I think research, industry, and academia, these are the communities that will have to come together for progress in additive manufacturing in Indonesia and everywhere else globally. So maybe I think last picture with Pandak as well, Chair, and Profang as well. Yeah, please. And Dr. Zaki Saldi, I think, please. All.
Pak Desmond, Scientific Committee.
Ya, Pak Desmond boleh, Pak. Pak Desmond, Scientific Committee, Pak.
Scientific Committee ikut, Pak.
Oh, iya. You'll take back your $300. All right.
Pak Desmond. Scientific Committee ikut Pak Zaki. Nomor saya.
Good. So, what about with like this or? Or this one? This one is one, is it? All right, thank you. Congratulations, all. Thank you so much. And with this, then that's all the events that we planned for this conference. I thank everybody for their participation. I think it's been great. We have research people, industry people, and academia that come together the last 2 days, and we talk about how we can make progress for additive manufacturing in research, in industry, as well as in academia, in Indonesia and globally everywhere else. With that, I think, Pak Andang, do you want to say something? Prof. Wang, maybe you want to say something a little bit? But maybe
maybe not too long because I
Yeah,
think
I know.
everybody's hungry for dinner now.
Okay, everyone is waiting for the dinner. Okay, I don't want to speak too much, but we have to say thank you for Alif to give us this opportunity to hold this conference in Indonesia. I thought he said that's the first time of the additive manufacturing related conference in Indonesia. And we believe that this kind of start point will be continued. We hope next year we will continue to hold conference in Indonesia. Okay, so that will be repeated every year. Okay, then this kind of story will be known to Indonesia's universities and to the government. Then they will give you more funding. So our university is supposed to have a good additive manufacturing systems and to cooperate with some other university overseas, not only inside Indonesia. Okay. Will that be okay? And by the way, I have to repeat again, possibly at the end of May, we are going to hold another ISA-AM, International Symposium on Additive Manufacturing in New Zealand, Queenstown. Okay, welcome to join. Okay.
Thank you. If Prof Wang say thanks to me, I actually now my turn is to thank Prof Pak Made, Pak Andang, Pak Made, especially. Where is Pak Made? And Pak Saki, and I think well, the last 1 month, I think we all have. We all work very hard. Actually, that it's almost amazing that final booklet is there, and you can have it, and it's I'm editing it like while I'm traveling to Jakarta actually. So and last but not least, roll drum please. This is all not gonna happen if not for Lazy. Lazy is please Lazy come. Lacy has been the one that already started working since like 6 months ago, mostly because I asked her to help me. So yeah, I think the secretariat of ISTA-AM is basically her. All the letters, all the receipts are basically her, and thank you very much for all the help, all the things that you have done. That booklet is actually her. Well, I do the conference program, but all the design, everything is actually Lacy. Do you want to say a few words?
I don't know if I have any.
All right, but thank you. I mean, for all these conferences because of you, of students in Udayana, Pak Made's team. Thank you all so much.
And the technical team.
Oh yeah, the technical team. Good team. All right, so I think with that, then we close this conference, and hopefully we'll have another year version, but probably not me as the chair. All right, thank you, everybody, and I think, Pandang, do you want to announce about the transportation?
We are going to go to Teba Cafe at Jimbaran. We hope everybody can join because we have plenty of space. So the technicality actually, Pamade knows more. We are going to travel by microbus, I think, or microbus, and then we are going there, and then we can enjoy atmosphere next to the sea. Unfortunately, no sunset because we already passed the sunset now. And also a bit cloudy, so not too good. Yeah, it's not too bad. So and after that, we are going back to this location also by bus. So we go together, we come back together. Okay, that's all. Thank you very much.
Umumnya semua udah? Sudah.
Udah ya? Semua pesertanya?
Iya sudah. Ada beberapa yang belum ngambil sih. Untuk tanggal. Oh ya ini aja sih.
Udah ya? Tanggal. Nggak semuanya saya tanggalin juga sih.
Sudah satu saja sih.
Udah ya?
Ya. Makasih Pak.
Ya, thank you ya. Terima kasih. Tadi nyala-nyala tapi baru sekarang bisa. Ya. Saya juga tadi nggak sempat ngelihat yang presentasi dari Bapak karena saya online. Baru datang. Iya. Oh, itu bilang tanggal 4 nggak bisa, jadi saya sempat pindah ke tanggal 5 bisa. Iya, itu. Udah ada sekarang.